quasars should not exist, at least not according to the simple expectations that come from everyday intuition about how bright an object can be, how fast black holes can grow, or how early complex structure should appear in the cosmos. And yet they do exist, blazing, violent, and so remote that the light we receive from them today began its journey when the universe was still young. A quasar is not a star nor a single exotic particle. It is the incandescent core of a galaxy in its most furious phase, a region where a supermassive black hole feeds with a ferocity that converts mass into outgoing power with astonishing efficiency. These engines can outshine the combined starlight of entire galaxies. They can emit across the electromagnetic spectrum from radio through infrared, optical and ultraviolet into X-rays and gamma rays, and they can be seen across most of the observable universe. The paradox at the heart of every quasar is simple and profound. The light we see, so bright it can blind an observer's attempt to see the host galaxy, emerges from gas and plasma that is spiraling into an object that itself emits no light. It is the drama of creation and destruction at the same place, the engine of darkness producing the brightest beacons we know. The discovery of quasars in the mid-20th century was a slow, tortuous shock to astronomy. Radio surveys found powerful sources. Optical follow-up showed compact, star-like points. Spectroscopy revealed emission lines at wavelengths that did not match any known laboratory pattern, unless those lines were shifted enormously to the red. Martin Schmidt's realization in 1963 that the odd spectral lines were ordinary transitions shifted by cosmological expansion reoriented everything. Those tiny-looking beacons were not nearby low-energy objects, but enormously distant furnaces. Their redshifts implied that they were billions of light-years away. Their apparent brightness then implied energy outputs beyond comprehension. For a while, astronomers resisted the conclusion. Could the redshifts be intrinsic and not cosmological? Could unknown physics be at play? But the weight of evidence accumulated, absorption features from intervening gas, the statistical distribution of redshifts, associations with host galaxies, and the community reached consensus. Quasars are extragalactic, extremely luminous, and powered by accretion onto supermassive black holes. Despite this consensus on the basic picture, the details are rich, messy, and still active research territory. The central engine is a black hole with millions to billions of solar masses. Matter from the surrounding galaxy loses angular momentum, falls inward, and forms an accretion disk. In the disk, gravitational energy is converted into heat by viscous processes, magnetic turbulence, and dissipation. Temperatures soar, particles accelerate, and intense radiation streams outward. A small fraction of that inflowing matter is collimated into relativistic jets that punch perpendicular to the disk and can extend for thousands or even millions of light years. The physics of how magnetic fields extract energy, whether primarily from the inflowing matter or from the black hole's spin via processes like Blandford-Znajek, are supported by simulations and observations, but remain areas of ongoing study. We know jets exist. We can map their interaction with interstellar and intergalactic gas, and we can infer that magnetic fields and relativistic effects are central to their formation. But the precise instrument of jet launching, the role of black hole spin distribution across cosmic history, and how jets survive coherence across enormous distances continue to inspire detailed theoretical and observational programs. One of the most pressing open puzzles quasars expose is their rapid appearance in cosmic history. We detect bright quasars when the universe is less than 1 billion years old. To reach masses of 1 billion suns in such short cosmological time appears difficult under simple models of black hole growth. by steady accretion. The observations are robust. The interpretation, how they grew so big so fast, is where hypotheses diverge. Several plausible scenarios exist. One is direct collapse, where a primordial gas cloud avoids fragmentation and collapses directly into a massive seed black hole of perhaps 4 to 10^6 solar masses. Another is hierarchical growth, where smaller black holes formed by population 3 star remnants merge and accrete rapidly in dense proto-galaxies. Still another invokes dense stellar clusters, where runaway collisions build up massive objects. Some speculative models even consider primordial black holes formed in the earliest instance of the universe. At present, no single mechanism has been definitively proven to explain all the earliest quasars, and this is precisely why these objects attract so much attention. They are signposts pointing toward physics of formation, accretion, and early structure that we have yet to fully decode. Beyond formation, quasars play a central ecological role in galaxy evolution. The energy they unleash is not confined to the nucleus. Radiation pressure, high-energy photons, and mechanical feedback from jets and winds can heat and expel gas from the host galaxy, altering the supply of fuel for star formation. This so-called quasar feedback is not just elegant theory, it is observed. Massive outflows have been measured in optical and X-ray spectra. Cold molecular gas has been found in high-velocity flows, and cavities carved by jets are visible in X-ray maps of cluster gas. The consensus view among galaxy formation modelers is that feedback from active galactic nuclei, including quasars, is required to produce the galaxy mass function we observe and to explain why the most massive galaxies are quenched in star formation. Still, how feedback couples to different gas phases, the efficiency of energy transfer, and the timescales over which a quasar switches on, regulates its host, and then peters out, remain active, quantitative questions. Observationally, quasars are invaluable cosmic probes. Their light travels through vast stretches of intergalactic medium before reaching us, and along the way it picks up absorption features, clouds of neutral hydrogen, heavy elements, and ionized gas that imprint a forest of spectral lines. The Lyman alpha forest in quasar spectra became the premier tool for tracing the distribution and ionization state of hydrogen at high redshift, revealing the structure of the cosmic web and mapping the ionization history of the universe. In the most distant quasars, we observe Gunn-Peterson troughs, near complete absorption by neutral hydrogen, providing direct evidence that the epoch of reionization was ending around the time those quasars shone. These measurements are strong, repeatable, and form a cornerstone of modern cosmology. They are robust ways to read the state of baryons between galaxies across time. Quasars also reveal themselves in radio and X-ray bands, and they come in different flavors. Some are radio loud, launching monster jets that light up their surroundings in radio frequencies. Others are radio quiet but luminous in optical and X-ray bands. Some quasars are obscured behind dust and gas, visible primarily in infrared and X-rays, while others are unobscured and shine clearly across the optical spectrum. This diversity is partly an orientation effect. An obscuring torus can hide the inner engine from some lines of sight, but it also reflects intrinsic differences in accretion rates, black hole spin, host galaxy environment, and perhaps evolutionary stage. Parsing this taxonomy is not mere categorization. It is a way to understand the physical processes that control how matter arrives at the nucleus, how efficiently it is converted into radiation, and how the engine interacts with its surroundings. Technological leaps are changing the quasar story fast. Infrared and submillimeter observatories, from space-based telescopes to ALMA, probe dust and molecular gas in quasar hosts, revealing both the fuel reservoirs and the winds that deplete them. High-resolution imaging with adaptive optics and space telescopes isolates host galaxies and maps their morphologies, merger histories, and star formation patterns. Time domain surveys are beginning to monitor quasar variability, offering clues to disk instabilities, microlensing by intervening stars, and even relativistic effects near the event horizon. And most dramatically, multi-messenger astronomy, combining electromagnetic data with gravitational waves, promises, in principle, to catch the most extreme mergers of massive black holes that might seed future quasars, although such detections at high redshift remain a frontier for future instruments, like space-based gravitational wave interferometers. It is also important, especially for public-facing narratives, to separate well-established facts from the more speculative or interpretive ideas. The observational facts are clear. Quasars are extremely luminous, extragalactic, powered by supermassive black holes, and visible across cosmic time. Their spectra and absorption features provide precise cosmological probes. Less certain are the details of the earliest seed formation, the precise microphysics of angular momentum transport and jet launching, and the ultimate connection between a single quasar's life cycle and the large-scale evolution of structure. These are not failures of science but invitations. They are where theory meets experiment and where new observations will force refinement or replacement of current models. Finally, there is the human aspect. Quasars transformed our cosmic perspective. They taught us that darkness and light are not opposites, but partners. The darkest objects, black holes, can produce the most luminous phenomena. They turned radio point sources into laboratories for extreme physics and made the early universe accessible through a single spectrum. They challenge our theories about how structure grows, how galaxies regulate themselves, and how gravity and electromagnetism collaborate near an event horizon. As new telescopes push deeper, as simulations become ever more realistic, and as theory matures, quasars will remain at the center of astrophysics, stubborn anomalies that have already rewritten parts of our cosmic story and that continue to demand answers. They are, quite literally, the blazing footprints of cosmic infancy, and their light will guide our science for decades to come. If you want to understand quasars, you must go deeper than their light. You must step inside the environment where they are born, the chaotic, violent, collapsing regions of early galaxies where gravity, turbulence, radiation, magnetic fields, and cosmic structure formation collide. A quasar does not simply turn on, it awakens. And its awakening requires conditions so rare and extreme that their very existence in the early universe forces scientists to reconsider many assumptions about how galaxies grow and how black holes behave. To understand these conditions, you must imagine what a galaxy looked like, not billions of years after the Big Bang, but mere hundreds of millions. The universe was smaller, hotter, denser, and far more crowded. Primitive galaxies were not the orderly spiral structures common today. They were turbulent, clumpy, collision-prone systems filled with immense clouds of gas, rapidly forming stars and tearing themselves apart as fast as they formed. This environment created natural funnels of material that spiraled toward the galactic center. Gravity pulled gas inward, turbulence stirred it violently, and collisions between clouds compressed dense pockets of matter. These were not slow processes. The early universe operated at fast pace. Everything, stars, galaxies, black holes, grew rapidly. But even in this frenetic environment, feeding a black hole to the point that it shines as a quasar requires an extreme, short-lived, extraordinarily efficient funneling of material. That funnel often begins with a merger. When two young galaxies collided, their gas clouds compressed, angular momentum redistributed, and vast amounts of matter were driven into the central region. The collision did not produce order, it produced chaos. But inside that chaos, the flow of material toward the nucleus became unstoppable. Gas spiraled inward, densities rose, and eventually the central black hole was overwhelmed with fuel. That moment, when supply meets demand at cosmic scale, created what humans today call a quasar. The term accretion sounds gentle, but accretion into a black hole in a young galaxy is anything but gentle. As matter falls inward, it forms a disk that can extend for light years. Every piece of gas within that disk accelerates to extraordinary speeds. Friction between layers of the disk heats them to temperatures hotter than the cores of stars. Collisions of particles strip electrons off atoms, creating a plasma. Magnetic fields thread through the disk, twisting, amplifying, and sometimes reconnecting violently. Shocks propagate outward, instabilities arise, spirals of gas thicken, compress and ignite with radiation. Yet despite the tremendous energy released, the disk remains trapped in rotation around the black hole because angular momentum prevents the gas from plunging straight inward. Only by losing that angular momentum can matter cross the event horizon. The mechanisms for that loss, magnetorotational instability, turbulence, viscosity, are complex and still being studied, but the result is simple. Once matter reaches the innermost stable orbit, it plunges into the black hole, converting a portion of its mass into pure energy. It is this conversion, not the black hole itself, that powers the quasar. To imagine the brightness of a quasar, you must abandon any natural comparison. Our Sun converts mass to energy through nuclear fusion with an efficiency of about 0.7%. A black hole accretion disk can convert mass into energy with efficiencies greater than 10%, and in some theoretical models involving rapidly spinning black holes, even higher. That means 1 kilogram of matter falling into an accretion disk can release more energy than the nuclear fusion of tens of kilograms of hydrogen. When billions of kilograms of matter fall in each second, the resulting luminosity rivals that of entire galaxies. The accretion disk becomes so bright that it outshines every star in the host galaxy combined. And because quasars emit across the electromagnetic spectrum, they illuminate the universe in wavelengths invisible to the human eye. X-rays from the inner disk reveal the highest energy regions. Infrared light shows dust heated by radiation. Radio waves trace jets and lobes extending across intergalactic space. The quasar becomes a multi-wavelength firestorm, visible across cosmic time. Yet for all this brilliance, the heart of the system remains forever dark. The event horizon allows no photons to escape. The region just outside it, where spacetime is twisted by the black hole's rotation, is the domain where some of the most extreme physics in the universe occur. It is here that jets are launched. The jets of quasars are among the greatest unsolved puzzles in astrophysics. Not because their existence is unknown, but because the details of their formation remain intricate and elusive. A jet forms when magnetic fields threading the accretion, disk and black hole get twisted by rotation, creating channels that accelerate charged particles outward at nearly the speed of light. These jets can carry mass and energy across distances far greater than the host galaxy itself. They plow into interstellar and intergalactic gas, heating it, compressing it, and sometimes triggering star formation while suppressing it elsewhere. The jets shape not only the quasar's environment, but also the long-term evolution of the galaxy. Observationally, jets are seen clearly in radio frequencies, sometimes forming symmetrical lobes on opposite sides of the quasar. These lobes store enormous energy and reveal how far the influence of a quasar can reach. But quasars are not just isolated events, they are part of a cosmic sequence, a chain of cause and effect that links the early universe to the structures seen today. The earliest quasars detected by telescopes like JWST and large ground observatories reveal that supermassive black holes formed astonishingly fast. Their existence suggests that the early universe was far more efficient at concentrating matter than previously realized. This contradicts some earlier expectations from galaxy formation models. forcing revisions to theories of gas cooling, fragmentation, and the collapse of primordial halos. In many simulations, black hole seeds struggle to grow to quasar size in the time available. Yet the observations leave no doubt. They were already massive when the universe was young. This mismatch between expectation and reality is one of the greatest scientific tensions in modern astrophysics. It is not a misunderstanding of data. The redshifts are measured accurately, the luminosities are confirmed, the identification of host galaxies is robust. The tension lies in the theoretical understanding of how something so massive can grow so fast in a universe so young. Part of the answer may lie in the density of the early cosmos. At high redshifts, matter was more tightly packed. Gas cools more efficiently when it is dense. Star formation happened at much higher rates. Massive star clusters formed and collapsed in ways rare in today's calmer universe. Collisions and mergers between young galaxies were frequent, creating turbulence that funneled matter inward. In such an environment, the seeds of supermassive black holes may have grown at rates unimaginable in the present era. Even if quasars today are quieter or less common, their ancient ancestors thrived in a context of abundance. This abundance, however, still does not completely solve the problem. If black holes grow too rapidly, they risk exceeding known theoretical limits, such as the Eddington limit, which describes the point at which radiation pressure from the accretion disk should push matter away faster than gravity can pull it inward. Yet some quasars in the early universe appear to challenge or even exceed these limits. Whether they did so through special conditions, episodic bursts, geometric effects, or new physics is still unclear. Scientists openly acknowledge this as an unresolved question. As the quasar brightens, the galaxy hosting it enters a phase of intense transformation. Radiation from the nucleus heats and blows out gas from the central regions. Winds accelerate outward at thousands of kilometers per second. Molecular clouds are shredded. Star formation slows or stops entirely. This feedback is essential for preventing galaxies from overgrowing. Without quasar feedback, theoretical models produce galaxies far more massive than observed. The regulation provided by the quasar ensures that the galaxy and its central black hole grow in tandem, a relationship supported by the observed correlation between black hole mass and the bulge mass of galaxies. However, while this correlation is well measured, the causal relationship remains debated. Does the black hole regulate the galaxy? Does the galaxy regulate the black hole? Or do they simply grow under the same conditions without directly influencing one another? Many simulations suggest feedback is crucial. Some observational studies show strong evidence of quasar-driven winds shaping galaxies. But the exact mechanisms remain active research, not settled science. Quasars also illuminate the cosmic web. As their luminous radiation travels across billions of light years, it encounters clouds of hydrogen gas scattered throughout intergalactic space. Each cloud leaves a tiny absorption line at a specific wavelength. The pattern of these lines, thousands at once, creates the Lyman alpha forest. This forest reveals the structure of matter between galaxies, mapping filaments, voids, and density fluctuations. Scientists use this data to refine cosmological models, measure the expansion rate of the universe, and study the Rayonization period when early stars and quasars Rayonize the cosmos. Without quasars, these measurements would be far more difficult. Their distant, bright nature makes them ideal backlights for studying the universe's invisible structures. Even the variability of quasars provides clues to their nature. Quasars flicker. They brighten and dim across months, days, or sometimes hours. This variability tells astronomers that the emitting region must be compact, no larger than the distance light can travel in that time. This alone confirms the central engine is extremely small on cosmic scales. For example, if a quasar brightens in one day, the region responsible cannot be larger than one light day across. This method allowed scientists to constrain the size of accretion disks long before direct imaging techniques existed. Today, the most advanced instruments, like interferometers, have begun to resolve structures near black holes more directly, but variability remains one of the oldest and simplest tools for probing quasar anatomy. Quasars, however, are not immortal. They fade. Once the supply of gas diminishes, the accretion disk thins and dims. The intense radiation declines, the jets weaken, the galaxy enters a quieter phase, where the central black hole still exists, but no longer dominates the galaxy's energy output. Most galaxies today, including the Milky Way, harbour dormant, supermassive black holes that may once have been quasars. Evidence from gamma-ray bubbles and relic outflows in the Milky Way suggests our galaxy experienced quasar-like episodes in the distant past. If any civilization lived near the centre of the Milky Way during that era, their sky would have been dominated by a radiant, terrifying beacon unlike anything visible from Earth today. The life cycle of a quasar tells a story of cosmic evolution, birth through mergers and inflows, life through furious accretion, and death through starvation. Yet every phase of this story raises new questions. Why do only some galaxies become quasars? Why do some quasars turn off quickly while others shine for millions of years? Why are some radio loud and others radio quiet? What controls the spin of the black hole, and how does that spin influence accretion efficiency? Scientific consensus exists on the general framework, but many detailed mechanisms remain under investigation. The interplay between observational data and theoretical modelling continues to refine our understanding. Quasars are the universe's brightest lighthouses, but they are also its deepest mysteries. They are the contradictions that inspire progress, the darkest engines producing the brightest light, the earliest structures revealing the universe's rapid growth, and the chaotic cores of galaxies shaping cosmic evolution. Their brilliance is not a symbol of stability, but of ferocity, the universe expressing its capacity for extremes. Quasars cannot be understood without understanding the machine that powers them, the accretion disk. This disk is neither a flat, calm structure, nor a uniform ring of glowing gas. It is a turbulent, chaotic, multi-layered, self-regulating system where gravity, magnetism, heat, shock waves, and relativity all collide. If you zoom into a quasar's center, not physically, but through the imagination guided by physics, you find a region where matter, falling inward from the host galaxy, forms a swirling structure of unimaginable energy. Gas clouds that once drifted quietly in the galaxy's outskirts are drawn inward over millions of years by gravitational torques, collisional interactions, or galactic mergers. As these clouds approach the center, their orbits tighten, speeds increase, and they are stretched, compressed, heated, and ionized. By the time the gas reaches the inner few light years, it is no longer a cold collection of atoms, but a plasma whipped into a storm. This storm becomes the accretion disk, a structure that transforms gravitational potential energy into radiation more efficiently than almost any known astrophysical process. The disk is not a solid surface. Any visual depiction that shows a smooth glowing ring is only a simplified representation. In reality, the disk is a churning environment with temperature gradients, density fluctuations, shocks, and instabilities. The outer regions may be relatively cool, only a few thousand degrees, allowing dust and molecules to survive. Closer inward, the temperature climbs into the tens of thousands, stripping electrons from atoms. Even deeper, near the innermost regions, temperatures reach millions of degrees, bright enough to produce X-ray radiation. The inner disk is so hot and luminous that it becomes opaque to its own light. Photons scatter off electrons countless times before escaping, creating a radiant fog of trapped light. radiation pressure becomes comparable to, or even exceeds, gas pressure in some regimes, shaping the structure of the disk. This balance between gas pressure, radiation pressure, gravity, and magnetic forces makes the accretion disk a complex, dynamic equilibrium that is constantly shifting. One of the surprising features of accretion disks is that despite their swirling motion, the material does not simply orbit forever. It spirals inward. This requires a mechanism for losing angular momentum. In classical physics, a disk of orbiting gas would not naturally spread or evolve. Each ring of gas would orbit indefinitely unless a torque acted on it. In quasars, that torque arises from turbulence, driven by the magneto-rotational instability, commonly called MRI. MRI is not a simple concept, but its discovery in the 1990s revolutionized accretion physics. In essence, if you place a weak magnetic field in a differentially rotating disk, the field lines connect fluid elements at different orbital speeds. The inner fluid tries to move ahead faster than the outer fluid, stretching the magnetic field lines and creating a tension that transfers angular momentum outward. This tension acts like a spring connecting two skaters on a rink. The inner one is pulled back, losing momentum, while the outer one is pulled forward, gaining momentum. In the accretion disk, this allows the inner gas to fall inward, while the outer regions move outward. This process creates turbulence, which heats the disk and drives continuous evolution. While MRI is widely accepted and supported by simulations, the detailed structure of the magnetic field, the saturation levels of turbulence, and the interaction between radiation and magnetic forces remain active areas of study. As matter moves inward, it encounters a region where relativistic effects dominate. The closer the gas is to the black hole, the more spacetime curvature distorts its path. The disk's inner edge is defined not by pressure or temperature, but by the innermost stable circular orbit, or ISCO, a purely relativistic feature. Inside the ISCO, circular orbits become impossible. Any gas crossing this boundary inevitably plunges into the black hole. The radius of the ISCO depends on the black hole's spin. For a non-spinning black hole, it is at 3 times the Schwarzschild radius. For a maximally spinning black hole, the ISCO can be as close as half the Schwarzschild radius. This difference dramatically affects the efficiency of energy extraction. A rapidly spinning black hole allows gas to radiate more energy before falling in, often resulting in brighter quasars. Because of this, scientists can estimate black hole spin by observing X-ray spectra or the shape of the broad ion emission lines produced in the inner disk. These methods are well established, though spin measurements are subject to uncertainties and model assumptions. Above the disk lies another critical structure, the corona. This is not a corona in the biological sense, or even like the sun's corona, though the analogy is partially useful. The quasar corona is a region of extremely hot, diffuse plasma hovering above the disk. It emits high-energy X-rays through inverse Compton scattering, where photons from the disk collide with relativistic electrons in the corona and gain energy. The shape of the corona, whether it is a compact region near the black hole or a more extended layer, remains an open question. Some models suggest a lamppost configuration, where a compact blob of plasma sits just above the black hole. Others propose that the corona is patchy, distributed, or linked to the base of the jets. What is solid is the observational evidence. X-ray emission is a hallmark of quasars, and rapid variability in X-ray-like curves suggests the emitting region is very small, sometimes no more than a few gravitational radii across. The jets of quasars arise from the innermost regions where magnetic fields interact with the spinning black hole. These jets are among the most spectacular phenomena in astrophysics. They are beams of plasma accelerated to near-light speeds and launched along the rotational axis of the black hole. They travel across interstellar and intergalactic space, carving cavities in gas, shocking clouds, generating radio lobes, and influencing their host galaxies on scales thousands of times larger than the accretion disk. While the general mechanism of jet launching is accepted, the extraction of energy from the rotating black hole via magnetic fields, the details remain complex. The strength of the magnetic field, the orientation of the disk, the black hole spin, and the surrounding environment all play roles. Jets provide one of the clearest links between black hole physics and galaxy evolution because their presence dramatically alters the flow of gas in the galaxy. Radio-loud quasars, which possess these enormous jets, are often found in massive galaxies and dense environments. Radio-quiet quasars, on the other hand, may still have small jets or outflows, but nothing like the colossally structured jets of their radio-loud counterparts. Even the broadline region of quasars reveals deeper complexity. As radiation from the disk illuminates gas clouds orbiting farther out, these clouds, moving at thousands of kilometers per second, emit broad emission lines. The widths of these lines provide a direct estimate of the gas velocity. Using these velocities and the radius of the emitting region, astronomers can estimate black hole masses with the virial method. This technique forms the basis of black hole mass measurements for thousands of quasars. While highly successful, it does rely on assumptions about geometry and gas distribution, meaning the method is accurate to within factors of a few rather than perfectly precise. Still, it provides the most practical approach for large quasar surveys. The accretion disk, corona, jet, and broadline region together form the engine of a quasar, but the fuel supply, the inflowing gas, determines how long the quasar shines. Inflows are not steady. They are episodic, chaotic, and influenced by the galaxy's environment. Galaxy mergers can provide massive bursts of fuel, resulting in luminous quasar episodes lasting millions of years. In quieter environments, the quasar may flicker as pockets of gas fall inward intermittently. Even in a single quasar's active lifetime, the brightness can vary dramatically. Observations have shown that some quasars change look, switching between high and low states, sometimes altering their spectral appearance so drastically that they appear to transform before our eyes. These transitions occur over years or decades, far faster than previously expected. They imply that accretion disks can undergo rapid structural changes, or that obscuring material can move into or out of the line of sight. While the observational evidence is strong, the underlying causes are not yet fully understood. If the accretion disk is the heart of the quasar, then the host galaxy is its body, and the relationship between the two is symbiotic. As the quasar shines, it reshapes the galaxy. Winds driven by the intense radiation can sweep gas out of the central regions, preventing further star formation. Jets can heat gas in the halo, suppressing cooling processes needed for star formation. This feedback is pivotal in modern galaxy evolution models. Without it, galaxies in simulations become too massive and form too many stars. While feedback is widely accepted, the precise coupling between quasar power and gas physics remains debated. Observations show large outflows of gas moving at high speeds, but whether these outflows remove enough material to quench star formation completely is still uncertain. Even the role of dark matter enters the story. Quasars form in massive dark matter halos, regions where gravity has assembled large-scale structures. These halos provide the potential wells that draw gas inward, setting the stage for galaxy formation and quasar ignition. Large surveys reveal that quasars prefer specific mass ranges of dark matter halos. This correlation helps scientists understand the connection between black holes and cosmic structure, showing that quasars are not isolated fireworks, but integrated parts of the cosmic web. The accretion process also creates unique observational signatures that allow scientists to test fundamental physics. Light from the inner disk undergoes gravitational redshift as it escapes the strong gravitational field. Ion emission lines in X-rays reveal broad skewed shapes, indicative of relativistic effects like Doppler boosting and frame dragging. These observations provide some of the most direct evidence for general relativity in the strong gravity regime. No myth or speculative idea is needed here. These are established, peer-reviewed results supported by multiple missions, including Chandra, XMM Newton, NuSTAR, and now JWST at other wavelengths. Despite all this progress, the accretion disk remains partly mysterious. Its exact structure, thickness, turbulence patterns, and radial energy transport mechanisms are topics of active research. Simulations improve each year, incorporating radiation hydrodynamics, magnetohydrodynamics, and relativity, but they are computationally expensive. Observations also face limits. Resolving the disk directly is impossible with current telescopes, except in the very nearest active galaxies. Instead, scientists infer structure from variability, spectra, and reverberation mapping, a technique that measures how different regions respond to changes in brightness. These indirect methods yield strong evidence, but still depend on modeling assumptions. Every part of the quasar, the disk, corona, jets, winds, and broadline region, forms an interconnected ecosystem powered by gravity and shaped by the laws of physics. None of these elements can be removed without collapsing the quasar model. And yet each remains a frontier in astrophysics, understood broadly, but filled with details that remain incomplete. Quasars are like perfect puzzles, where most of the outer pieces are firmly in place, but the inner structure still requires refinement. A quasar never lives in isolation. It is born inside a galaxy, fed by a galaxy, shaped by a galaxy, and ultimately capable of reshaping that galaxy in return. If the first three parts reveal what a quasar is, then this part reveals what a quasar does, how it alters everything around it, from the stars nearest its center to the vast halos of gas that surround the entire galaxy. A quasar is not a light bulb quietly burning. At the core, it is a storm, a furnace, an engine, powerful enough to heat, push, tear, or destroy material across distances measured in tens or even hundreds of thousands of light years. And astonishingly, without this destructive violence, galaxies might not look anything like the structures we see today. To understand the modern universe, you must understand quasar feedback, the process by which a black hole's energy output affects the evolution of its host galaxy and the wider cosmic environment. Imagine a galaxy in the early universe. It is filled with dense gas clouds, chaotic star formation, and turbulent flows shaped by repeated mergers. As the central black hole ignites into a quasar, the radiation pressure created within the accretion disk becomes immense. Photons streaming outward do not simply illuminate the galaxy, they push. They exert real force on the gas around the nucleus. When this radiation pressure exceeds the gravitational pull holding gas near the center, the gas is driven outward in colossal winds. These winds can accelerate to thousands of kilometers per second, sweeping material from the galaxy's heart into the halo, and in some cases, entirely out of the galaxy. This process has been measured directly. Astronomers observe broad absorption lines in quasar spectra indicating gas moving outward at extreme speeds. These outflows, seen repeatedly across different telescopes and wavelengths, are not hypothetical. They are established observational phenomena. But quasar winds are only part of the story. The jets of quasars, those narrow relativistic beams emerging from the poles of the black hole, carry energy far beyond the central region. A jet can punch through the galaxy's gas, drilling channels and inflating enormous cavities in the halo. In galaxy clusters, jets inflate bubbles in the surrounding hot plasma, cavities so large that they can be detected hundreds of millions of years after the jets stop. These cavities demonstrate beyond doubt that jets transfer enormous amounts of mechanical energy into their environment. The mechanical power of such jets can easily exceed the radiative output of the quasar itself. Even though only a minority of quasars produce strong jets, those that do can profoundly alter their host galaxies and surrounding clusters. The scientific consensus is firm here. Radio jets heat surrounding gas, suppress cooling, and regulate star formation. Observations from X-ray telescopes, such as Chandra, have repeatedly confirmed this effect. Winds and jets work together, sometimes simultaneously, sometimes in alternating phases, to regulate the growth of the galaxy. This regulation is crucial because without it, galaxies in simulations grow far too massive. They form too many stars and reach sizes inconsistent with actual observations. For decades, this discrepancy was a major problem in cosmology. Only when quasar feedback was incorporated into models did galaxy formation begin to resemble what we see in surveys. In this sense, quasars are not anomalies. They are essential components of cosmic evolution. They act as thermostats for galaxies, preventing runaway star formation by removing or heating the gas that would otherwise have cooled and collapsed into new stars. One of the most striking pieces of evidence for quasar feedback is the tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. This relationship, known as the M-sigma relation, shows that galaxies and their central black holes grow together. Yet the black hole itself is far too small to influence the stars directly through gravity. Its sphere of influence typically extends only a few parsecs. This means the correlation must arise from a regulatory process capable of reaching across large distances. Quasar feedback provides that mechanism. Winds and jets redistribute energy and momentum across the galaxy, linking the growth of the black hole to the growth of the galaxy's stars. The correlation is observationally robust, accepted by the scientific community, and one of the strongest indications that galaxies and black holes co-evolve. But while the correlation is real, its interpretation is not fully settled. Do black holes regulate galaxies? Do galaxies regulate black holes? Or do both grow under the same global conditions imposed by the dark matter halo? These questions are debated. Some models suggest black hole feedback drives the relationship by sculpting star formation. Others propose that galaxies supply fuel to the black hole at rates determined by their structure, and the correlation is simply a byproduct of this shared supply. Still others argue that the dark matter halo dictates the dynamics of both systems. While the evidence for feedback is strong, the exact causal link remains an active research frontier, with new data from the JWST and future observatories expected to refine the picture. Beyond the scales of individual galaxies, quasars influence the intergalactic medium, the vast, diffuse gas that fills the space between galaxies. As quasar light travels across billions of years, it carries information about everything it passes through. But more importantly, a quasar can heat and ionize gas far outside its galaxy, extending its influence over enormous distances. In the epoch of reionization, the time when the first stars and galaxies reionized the universe's hydrogen, quasars played a significant role. Although stars contributed the bulk of the ionizing photons, quasars added additional high-energy radiation that helped reionize helium and create transparent channels in the intergalactic medium. Observations of quasar proximity zones, regions around quasars where the gas is highly ionized, provide direct evidence of their cosmic influence. These zones act like bubbles carved into the intergalactic medium, revealing how far a quasar's radiation can travel before being absorbed by neutral hydrogen. Quasars also impact the structure of the cosmic web. Filaments of dark matter and gas form the backbone of cosmic structure. Quasars are often found at the intersections of these filaments, regions of high density where material flows inward. Their energetic output can heat gas within these filaments, altering cooling rates and affecting how smaller galaxies form along these structures. While this influence is less direct than the effects within the host galaxy, Simulations suggest that quasar activity helps shape the thermal history of the intergalactic medium. These large-scale effects are still being studied, and while the existence of quasar impact on cluster and filament environments is supported, the quantitative details remain a developing science. On the largest scales, quasars serve as markers of cosmic evolution. Their distribution across redshift provides insight into the growth of structure, the availability of cold gas, and the evolution of galaxy merger rates. Quasar populations peak around 10 billion years ago, a period known as cosmic noon, when star formation and black hole growth were at their highest. After this era, quasar numbers decline as galaxies exhaust their gas supplies or settle into more stable configurations. This trend is well supported by surveys and is one of the clearest signatures of the universe transitioning from a turbulent, gas-rich epoch to the more structured and quiescent universe seen today. In addition to reshaping galaxies and large-scale structures, quasars serve as powerful natural laboratories for testing fundamental physics. Their extreme environments allow scientists to probe the behavior of matter under conditions that cannot be reproduced on Earth. For example, X-ray reflection spectroscopy reveals how photons travel through regions of spacetime distorted by relativity. Line shapes are stretched, skewed, and shifted by gravitational redshift and Doppler boosting. This provides direct evidence for general relativity in the strong field regime. Observations of quasar microlensing, where stars in an intervening galaxy magnify small regions of the quasar, allow astronomers to study the structure of the accretion disk at micro-arcsecond scales. The Lyman alpha forest in quasar spectra maps the distribution of matter across billions of light-years and provides one of the best measurements of the universe's baryonic content. None of these tools would exist without quasars. They are cosmic probes, shining flashlights across the universe's vast landscape. But not all quasar effects are destructive. In some cases, quasar-driven shocks can trigger star formation instead of suppressing it. When an outflow compresses gas clouds in a galaxy's outer regions, new stars can ignite. These episodes of positive feedback are less common, but supported by observations of star-forming rings and high-pressure environments near quasar-driven shocks. The idea that a black hole can both kill and create stars may seem contradictory, but the universe often operates through dualities. As with many astrophysical processes, the outcome depends on the environment, density, and velocity of the gas. Positive feedback is a minority channel, but it remains an intriguing part of the larger story. Even as quasars shape the cosmos, they are shaped by their own limitations. A quasar cannot blow out all its gas indefinitely. If feedback becomes too strong, the quasar effectively starves itself by removing the very material that feeds it. This self-limiting process creates natural duty cycles, periods of activity, followed by periods of quiet. These cycles may recur many times over a galaxy's lifetime, each episode altering the galaxy in subtle or dramatic ways. Evidence of such cycles appears in light echoes, fossil outflows, and relic lobes from past activity. Some galaxies show signs of multiple quasar episodes separated by millions of years. These cycles are reminders that quasars are not static engines, but dynamic participants in the long narrative of galaxy evolution. Stepping back, one sees a remarkable coherence emerging, despite the staggering complexity. Quasars, by releasing energy from the smaller scales near a black hole, control processes on scales a million times larger. A disk no larger than a solar system can influence a galaxy spanning hundreds of thousands of light years. A jet no wider than a light week at its base can inflate cavities larger than entire galaxy clusters. Photons emitted near an event horizon can travel billions of years to shape the ionization state of intergalactic gas. This chain of influence from micro to macro is one of the most stunning displays of interconnected physics in the universe. The laws governing the motion of plasma near a black hole ripple outward to sculpt the architecture of cosmic structures. Quasars reveal a universe that is not passive but responsive. Gravity collapses matter inward, fueling the quasar. Radiation pushes outward, opposing gravity. Gas cools and condenses into stars, but quasar feedback heats and scatters it. The cosmic web supplies material to galaxies, but quasars redistribute that material. In every direction, quasars sit at the crossroads of processes that define the universe. They are not merely bright objects, they are engines of cosmic engineering. This is why quasars remain central to astrophysics. They explain why galaxies stop forming stars, why black holes correlate with bulge mass, why massive galaxies are rare, why reionization occurred as it did, and even how the universe transitioned from a youthful frenzy to the structured cosmos we observe. They are both actors and archivists, shaping their environment while preserving in their spectra the record of all they have touched. When we look at a quasar, we are not just looking at a bright object in the sky. We are looking back through time, peering across billions of years of cosmic history, witnessing the universe as it existed when it was young, raw, turbulent, and unrecognizable compared to the structured cosmos we inhabit today. Light from quasars has traveled so far, through so many epochs, that each photon carries with it a detailed record of the universe's evolution, its temperature, its composition, its density, its expansion rate, and its distribution of matter. A quasar is not just a distant beacon, it is a time machine, a cosmic archive, a window into eras long before Earth formed, before the Milky Way assembled, before the universe became transparent. When astronomers observe quasars, they're extracting information not only from the quasar itself, but from everything that light encountered on its journey. Clouds of hydrogen, filaments of the cosmic web, pockets of dark matter, ionized regions shaped by early stars, and the expanding fabric of spacetime. The extraordinary distances involved in quasar observations mean that we are seeing the universe at multiple stages simultaneously. Some quasars are so distant that we see them as they existed when the universe was less than 1 billion years old, while others represent later stages of cosmic evolution. The farther the quasar, the farther back in time we look. This makes quasars some of the most valuable tools for studying the early cosmos. They reveal the conditions under which the first galaxies formed. They map the reionization era. They trace the chemical enrichment of the universe, and they provide measurements of expansion across cosmic time. One of the clearest examples of this time travel effect is the Lyman alpha forest, a dense forest of tiny absorption lines in a quasar spectrum caused by clouds of hydrogen gas scattered along the line of sight. Each hydrogen cloud absorbs light at a precise wavelength, but because each cloud exists at a different distance and therefore a different redshift, the absorption lines shift accordingly. This creates a layered record of the universe's structure across billions of light years. The Lyman alpha forest is not a hypothesis. It is one of the most robust observational tools in cosmology, used to map density fluctuations, measure the distribution of matter, and test models of cosmic evolution. It reveals that the universe is not homogeneous, but structured like a web, with filaments of dark matter and gas connecting galaxies. These filaments grow over time, shaped by gravity, and quasars let us see their evolution directly. As light from a distant quasar passes through these cosmic structures, it becomes an X-ray or ultraviolet fingerprint of the universe's skeleton. Quasars also reveal the ionization history of the universe. After the Big Bang, the universe cooled until hydrogen atoms formed, making space opaque to ultraviolet light. Only when the first stars, galaxies, and quasars ignited was the hydrogen reionized. This reionization era is a defining chapter in the universe's evolution, marking the transition from cosmic darkness to cosmic transparency. Some of the most distant quasars show Gunn-Peterson troughs, regions in their spectra where the light is almost entirely absorbed by neutral hydrogen. These troughs are direct evidence that the universe was not fully reionized at the time that Quasar emitted its light. Each newly discovered high redshift quasar adds data points to map when and how quickly the universe became ionized. Quasars provide the only direct observational window into the final stages of reionization. While the stars in early galaxies provided most of the ionizing photons, quasars, because of their intense ultraviolet and X-ray output, helped ionize helium and create transparent bubbles through which later light could travel. The current scientific consensus is that quasars were secondary contributors to hydrogen reionization, but primary drivers of helium reionization. This distinction is important and well supported by observations, though the precise contributions of different source populations continue to be studied. In addition to revealing the universe's ionization history, quasars also trace the chemical evolution of cosmic gas. As quasar light passes through intergalactic matter, it encounters atoms of carbon, oxygen, silicon, iron, and other elements produced by earlier generations of stars. The relative strengths of absorption lines reveal when these elements first appeared and how abundances increased over time. Quasars therefore provide insight into when the first stars formed, exploded, and enriched the cosmos with heavy elements. One of the surprising findings from quasar absorption studies is that even very early galaxies show significant metal enrichment. This suggests that star formation and supernova feedback began extremely early and rapidly. The presence of metals in the early universe is not speculative, it is observed repeatedly in quasar absorption systems. What remains uncertain is the exact mechanism and timescale of enrichment, but the direction of progress is clear. The universe matured faster than older models predicted. Quasars are also essential for measuring the universe's expansion rate. Their redshifts provide information about cosmic distances, and when combined with other cosmological probes, supernova, baryon, acoustic oscillations, and the cosmic microwave background, they help refine estimates of cosmological parameters. Although quasars are not standard candles like Type Ia supernova, newer methods attempt to use quasar variability or emission line properties as distance indicators. These methods are still in development and are not yet part of the scientific consensus, but they represent promising efforts to transform quasars into cosmological rulers. A well-known speculative idea is that quasars might help resolve the Hubble tension, the disagreement between expansion rates measured from the early and late universe. Some researchers propose that quasar-based techniques could provide independent measurements, bridging the gap between the two regimes. This concept remains unproven, but the research community is actively investigating it. Another way quasars act as time machines is through gravitational lensing. When a massive object, such as a galaxy or cluster, lies between a quasar and Earth, its gravity bends the quasar's light. This can produce multiple images, arcs, magnifications, or distortions. These lensed quasars allow scientists to measure the mass distribution of the intervening object, including dark matter. Time delays between lensed images, caused by light traveling along different paths, provide a way to measure cosmological distances. This technique is well established and provides one of the cleanest ways to probe dark energy. Lensed quasars therefore reveal not only the distant past but also the invisible structures in the present universe. They show where dark matter is located and how much of it exists in different environments. Unlike speculative dark matter theories, the existence of lensing effects is not debated. They are observed directly in hundreds of systems. What remains uncertain are the particle properties of dark matter, not its gravitational influence. In the realm of extreme physics, quasars allow scientists to test ideas about quantum mechanics, general relativity, plasma physics, and high-energy astrophysics. light echoing through dust around quasars, can reveal the geometry of the central engine. Polarization patterns can uncover the structure of magnetic fields. X-ray reverberation, where echoes of flares bounce off the inner disk, gives clues about spacetime near the black hole. These observations probe regions where gravity is so strong that Newtonian physics fails entirely. Even the variability of quasars provides clues about physical processes occurring on scales of hours to weeks. Quasars have been observed to dim or brighten dramatically over short periods. Some changing-look quasars undergo spectral transformations that were once thought impossible on such short timescales. These changes indicate that accretion disks can reorganize themselves rapidly, or that obscuring material can move in and out of the line of sight much faster than predicted. These episodes challenge previous assumptions and indicate that quasar life cycles are dynamic, not static. Because quasars span a huge range of distances, masses, luminosities, and environments, they provide a continuous record of cosmic evolution. The earliest quasars reveal how the first structures formed. Intermediate quasars trace the peak of galaxy and black hole growth. Later quasars show how galaxies transitioned into quieter states. This continuity makes quasars unique. They are the only objects that are both bright enough and long-lived enough to map the universe from its infancy to its maturity. Even though their activity phases are short on cosmic timescales, the population of quasars over billions of years reveals the universe's ongoing transformations. Cosmological surveys using quasars like SDSS, DESI, and future Euclid and Roman observatories use them as markers to build three-dimensional maps of the cosmos. These maps reveal large-scale structures, voids, walls, and superclusters. The distribution of quasars also provides insight into dark matter halos, showing that quasars tend to reside in specific mass ranges and environments. This correlation is well supported and helps scientists understand how black hole growth relates to hierarchical structure formation. In addition to their scientific role, quasars carry philosophical implications because of their time-traveling nature. When we see a quasar, we see a galaxy as it was billions of years ago. That galaxy may no longer host a quasar. It may be extinct. It may have merged with another galaxy. Its black hole may be dormant. The quasar we see is a ghost from the past, a bright memory of a vanished moment. Observing quasars forces us to confront the fact that the universe we see is not the universe that exists now. Light from distant objects shows the past, not the present. This disconnect between appearance and actuality challenges human intuition about reality. In a cosmic sense, the present moment is invisible beyond a few thousand light years. Everything farther away is ancient history. This perspective turns the night sky into a museum of fossilized light. The deepest irony is that quasars, which appear as tiny points, reveal some of the largest truths about the universe. They show that structure forms early. They show that black holes grow fast. They show that galaxies evolve violently. They show that cosmic ionization was patchy. They show that matter between galaxies is not empty, but structured. They show that dark matter sculpts the cosmic web. They show that light can trace the expansion of the universe. A single quasar spectrum contains more information about the cosmos than nearly any other type of astronomical data. Their usefulness spans chemistry, physics, cosmology, relativity, and even the search for fundamental constants. Some studies test whether constants, such as the fine structure constant, have changed over time by analyzing quasar spectra. While the current consensus is that constants have remained stable, this remains an active area of investigation, with some studies hinting at tiny variations. These hints are not confirmed and remain speculative, but quasars provide the only feasible way to test such questions across cosmic time. The role of quasars as time machines becomes even more dramatic when considering the future. As telescopes grow more powerful, especially infrared observatories like JWST, we will detect quasars even farther back, perhaps within 200 million years of the Big Bang. These earliest quasars will challenge all current models and demand new explanations for how massive black holes form so quickly. They will reveal the earliest galaxies and test theories of dark matter particle behavior. They will refine the timeline of reionization and illuminate the transition from primordial simplicity to cosmic complexity. In this sense, quasars do not only reveal the past, they also shape the future of astronomy. Quasars are among the most thoroughly studied objects in astronomy, and yet they remain among the most mysterious. The more scientists learn about them, the more questions appear. They sit at the intersection of galaxy evolution, high-energy physics, black hole growth, cosmology, and even the search for new physics beyond the standard model. Their extreme luminosity, their rapid variability, their powerful jets, and their improbable appearance early in cosmic history all combine into a puzzle that is still far from complete. It is tempting to think of quasars as solved phenomena simply because their broad features are known: accretion disks, supermassive black holes, winds, jets, and feedback. But these pieces leave gaps where our understanding fades. Part of what makes quasars so fascinating is that they are both familiar and alien. Familiar enough to model with physics, alien enough to expose the limits of current theories. To appreciate how much remains unknown, one must examine the puzzles scientists are still struggling to solve, the tensions between observation and theory, and the phenomena that defy easy explanation. The first major mystery concerns the origin of supermassive black hole seeds. Observations show quasars shining less than 1 billion years after the Big Bang, powered by black holes already reaching billions of solar masses. Growing such enormous black holes in such a short time poses a problem. Under ordinary conditions, a black hole's growth is limited by the Eddington rate, the point at which radiation pressure counters gravitational infall. Yet early quasars seem to require growth rates that push, strain, or exceed this theoretical limit. One solution is that the initial seeds of these black holes were unusually massive, perhaps forming through the direct collapse of giant gas clouds that never fragmented into stars. This idea, known as the direct collapse black hole model, is widely explored in the scientific community. It remains a hypothesis, not a proven mechanism, but it helps explain how massive seeds could jumpstart the growth of early quasars. Another possibility is that early stars were much larger and more unstable than stars today, collapsing into black holes of hundreds of solar masses, which then merged rapidly. This cluster-driven growth model is also plausible, but not confirmed. A more speculative idea is that primordial black holes formed during density fluctuations in the first seconds of the universe. This idea is intriguing but lacks direct observational support and is considered speculative rather than established science. The unresolved question persists: how did the universe create monster black holes so early? Every new distant quasar discovered pushes this question further, tightening the constraints and increasing the urgency to find a coherent explanation. The second major mystery involves super-Eddington accretion, growth that appears to exceed the maximum allowed by theoretical radiation pressure. The Eddington limit is a cornerstone of astrophysics, yet some quasars appear too luminous or too massive to have grown at a steady Eddington rate over cosmic history. One possibility is that quasars grow in short bursts of super-Eddington accretion, where gas flows so rapidly inward that radiation becomes trapped and dragged across the event horizon. In this scenario, radiation pressure does not halt accretion. Instead, radiation is advected inward rather than escaping. This photon-trapping regime is predicted in some models, and simulations support its plausibility, but observational proof remains difficult. Another idea is that the geometry of the accretion disk allows radiation to escape along the poles, reducing the effective radiation pressure on the infalling gas. This would permit faster accretion rates without violating physical laws. Whether this occurs in actual quasars remains unproven, but it is consistent with some observations of anisotropic emission in high redshift quasars. The truth may involve multiple mechanisms operating together. What is established is that quasars must have grown rapidly. What is uncertain is exactly how they overcame physical limits to do so. A related mystery is how quasars maintain stability while producing enormous luminosity and turbulence. Accretion disks should, in theory, be unstable. They should puff up, collapse, fragment, or lose coherence under the overwhelming forces acting upon them. Yet quasars operate for millions or tens of millions of years with remarkable efficiency. Why? Theoretical work points to magneto-rotational instability as the primary driver of angular momentum transport. But simulations are limited by computational constraints. They can model small patches of disks or short timescales, but cannot yet simulate entire disks in full detail over quasar lifetimes. This leaves open questions. Why do some quasars show stable emission, while others flicker dramatically? What controls the thickness of the disk? Why do some disks produce strong winds, and others do not? Why do some quasars launch massive jets, while others remain radio quiet? The existence of these phenomena is confirmed, but their controlling parameters remain unknown. Jets themselves remain among the most profound mysteries in astrophysics. How can a black hole, a region with no internal structure and from which no material can escape, produce collimated beams of plasma moving at nearly the speed of light? The leading explanation involves magnetic fields extracting rotational energy from the spinning black hole, but the detailed process is not fully resolved. Simulations show that jets require strong, organized magnetic fields threading the event horizon, but where do these fields come from? How are they maintained? Why are jets stable across distances far larger than their launch region? Why do some jets bend and precess while others stay straight? Observations show that jets can remain coherent across millions of light years, a scale so absurdly disproportionate to their origin that it seems to violate intuition. And yet the evidence is clear. Radio lobes, X-ray knots, and synchrotron emission all testify to the existence of these cosmic accelerators. Jets are also implicated in heating galaxy clusters, regulating star formation, and shaping large-scale structure. Despite decades of research, their full physics still resides at the frontier of astrophysics. Another mystery lies in the phenomenon of changing-look quasars, objects that dramatically alter their appearance over surprisingly short timescales. These changes can involve shifts from a bright quasar state with broad emission lines and strong continuum emission to a faint, galaxy-dominated state, or vice versa. These transformations occur over years or decades, far too quickly to be explained by the slow processes traditionally associated with accretion disks. Scientists propose several possibilities: sudden changes in accretion rate, rapid reconfiguration of the disk, obscuring clouds moving into the line of sight, or instabilities in the corona. The cause is still debated and currently an open problem. What is certain is that quasars are more dynamic than previously believed. Their variability challenges assumptions about how stable accretion disks should be, and suggests that quasar life cycles may involve rapid transitions rather than slow evolution. One of the most profound open questions relates to the connection between quasars and their host galaxies. While it's widely accepted that quasars influence galaxy growth, the detail of how they do so remains unclear. Why do some quasars quench star formation, while others trigger it? Why do some galaxies with massive black holes never experience quasar activity? Why do some merger-driven galaxies ignite quasars, while others remain quiet? Observations show that quasars often appear in galaxies undergoing mergers or interactions, but not always. Some quasars live in isolated galaxies with no evidence of recent disturbance. Moreover, the observed correlation between black hole mass and galaxy bulge mass is well established, but the causality remains murky. It is known that quasars release enough energy to influence their galaxies, yet the exact coupling between radiation, jets, winds, and galactic gas remains unresolved. This is one of the most active areas of research in extragalactic astronomy. Another unsolved aspect concerns the chemical composition of quasars. Some quasars exhibit unexpectedly high metallicity, levels of heavy elements far exceeding what one might expect for galaxies so early in cosmic history. This suggests that star formation and supernova activity were extremely rapid and efficient in the early universe. But how did galaxies enrich themselves so quickly? Were early stars more massive or more numerous than expected? Did feedback processes accelerate enrichment? While the presence of metals is observationally confirmed, the mechanism of enrichment remains speculative. This finding forces scientists to revisit models of early star formation, nucleosynthesis, and galaxy assembly. Quasars also raise deep questions about the behavior of dark matter. They appear to reside in massive dark matter halos, but the exact masses and environments vary across observations. If dark matter behaves differently than expected, or if multiple species of dark matter exist, quasars may reveal discrepancies in halo mass estimates, clustering patterns, or absorption signatures. Some speculative research explores whether dark matter interactions could influence black hole growth or quasar fueling. These ideas remain exploratory and are not part of consensus physics, but quasars provide one of the few observational windows into such possibilities. At the boundary of cosmology and fundamental physics, quasars contribute to testing the stability of physical constants over time. The fine structure constant, which governs electromagnetic interactions, can leave subtle imprints in quasar absorption lines. A handful of studies have reported hints that this constant might vary slightly across cosmic distances, while others find no such effect. These results are controversial and not accepted as proven. The current consensus is that if variations exist at all, they are extremely small and not yet confirmed. Still, quasars remain the only practical tool for probing this question over billions of years. Perhaps the greatest mystery, however, is philosophical more than physical. Quasars embody the duality at the heart of cosmic evolution. They reveal a universe capable of creating structures of extraordinary order, accretion disks, jets, emission regions, inside environments of absolute chaos. They show how small, compact regions can influence vast galactic and intergalactic scales. They show how black holes, often imagined as destructive, serve as engines of creation, shaping galaxies and influencing the cosmic web. They show how the universe transitions from simplicity to complexity, from darkness to radiance, from primordial gas to galaxies capable of hosting life. And yet quasars also challenge the elegance of our theories by existing at extremes that strain those theories. Every unresolved mystery pushes science forward. The unknown seed masses force new models of early cosmic structure. The super-Eddington tension forces refinements in accretion theory. The stability of jets challenges plasma physics and relativity. Changing look quasars push understanding of disk dynamics. High redshift quasars push models of galaxy formation. Metallicities push models of star formation. Quasars not only illuminate the universe, they push the boundaries of knowledge itself. And as powerful as modern telescopes are, the story is only beginning. The next decade will bring deeper surveys, higher resolution spectra, new time domain monitoring, and multi-messenger data. JWST, Euclid, Roman, SKA, and next-generation X-ray observatories will reveal quasars farther away, smaller in mass, more primitive, more unusual, more extreme. Each new discovery will expose new tension between theory and observation. A quasar is not a permanent state. It is a phase, a luminous eruption in the life of a galaxy, and like every living thing that burns bright, it eventually fades. To understand the life cycle of a quasar, one must step away from the image of a black hole as a fixed entity and instead imagine it as something more dynamic, an engine whose fuel supply fluctuates, whose environment evolves, and whose energy output waxes and wanes across millions of years. The birth of a quasar is violent, its maturity brilliant, and its death quiet, leaving behind a dormant supermassive black hole that may one day awaken again under the right conditions. This life cycle is not smooth or predictable. It is governed by chaos, galaxy collisions, gas inflows, angular momentum transport, starbursts, outflows, winds, and the slow gravitational ballet of cosmic structure formation. And yet, beneath this chaos lies a narrative thread. Quasars grow alongside their galaxies, shaping and being shaped by the environments that host them. Their life cycles reveal how galaxies evolve, how black holes gain mass, and how the universe transitions from a youthful frenzy to the mature structure seen today. The beginning of a quasar's life almost always involves an inflow of gas toward the galactic center. This inflow rarely occurs spontaneously. It must be triggered by an event powerful enough to overcome the stabilizing forces that normally keep gas in orbit. Angular momentum, pressure gradients, and the gravitational pull of stars in the disk. Galaxy mergers are one of the most efficient ways to drive gas inward. When two galaxies interact, their gravitational fields twist and distort each other, creating tidal torques that strip angular momentum from gas clouds. These clouds, now with less rotational support, begin spiraling toward the nucleus. Observational evidence supports this link. Many quasars appear in galaxies with signs of past or ongoing mergers, distorted shapes, tidal tails, double nuclei, or starburst activity. This connection is not universal, however. Some quasars reside in isolated galaxies with no clear signs of disturbance, indicating that internal processes, such as disk instabilities or bar-driven inflows, can also deliver gas to the central black hole. While mergers are common quasar triggers, they are not the only mechanism. This diversity is part of the evolving scientific understanding of quasar activation. As gas flows inward from kiloparsec scales to parsec scales, it compresses, shocks, and heats, sometimes triggering starbursts. These starbursts consume some of the gas but also enrich the environment with metals through supernova explosions. The enriched gas, now more efficient at cooling, sinks even deeper. Eventually, a portion of this gas reaches regions close enough to the black hole for accretion to begin. At this point, the inflow transitions into an accretion disk, and the black hole's luminosity begins to rise. Before the quasar fully ignites, it may pass through a phase known as a Seyfert galaxy, or active galactic nucleus, with moderate luminosity. These are transitional stages, representing the black hole warming up before reaching its full quasar brilliance. Once the quasar enters its peak phase, it becomes one of the most luminous objects in the universe. Its accretion disk radiates intensely across all wavelengths. Jets, if present, pierce the galaxy like spears of relativistic plasma. Winds peel gas away from the nucleus. The quasar's radiation begins to reshape the galaxy around it, sending shockwaves into the interstellar medium. This peak phase does not last long in cosmic terms, typically a few tens of millions of years. While this duration is an estimate with some uncertainty, the general consensus is that quasar lifetimes are relatively short compared to the age of galaxies. During this time, the black hole accumulates most of its mass. If it began with 1 million solar masses, it might grow to 1 billion. If it began with 10 million, it might grow to several hundred million. This growth is not steady, and observations of variability suggest that accretion rates fluctuate dramatically, driven by instabilities, magnetic fields, and changes in fuel supply. As the quasar shines, it creates a feedback cycle. Radiation pressure pushes gas outward, heating or expelling it. This reduces the amount of gas available for continued accretion. Jets carve tunnels through the galaxy, pushing gas aside and creating cavities. Outflows driven by the quasar's wind-sweep material away from the center. These processes eventually choke the quasar by cutting off its fuel supply. This self-limiting cycle is one of the reasons quasars do not shine indefinitely. The black hole cannot sustain its energy output if it destroys the very gas it needs to feed on. This coupling between quasar activity and the depletion of gas is supported by observations. Galaxies hosting quasars often show signs of gas loss, star formation decline, or shocked structures consistent with outflow-driven clearing. The decline of a quasar is rarely abrupt. It resembles the fading of a fire as fuel is exhausted. The accretion disk gradually loses mass, becoming thinner and less luminous. Emission lines weaken, winds and jets diminish. The quasar may flicker on and off as pockets of gas temporarily revive the accretion disk, but the overall trajectory is downward. Some quasars undergo dramatic dips in brightness due to sudden drops in accretion rate or the passage of obscuring clouds. These changing-look quasars illustrate that quasar decline is not a smooth descent but a chaotic tapering influenced by many small-scale processes. Over a period of millions of years, the quasar fades into a much dimmer active galactic nucleus or shuts down entirely, leaving behind a dormant supermassive black hole. This dormant phase can last billions of years. The black hole remains massive, silent, and gravitationally dominant, but with little or no accretion. The Milky Way's central black hole, Sagittarius A, provides a clear example. Today it is quiet, emitting only faint radiation compared to a quasar. Yet evidence suggests it experienced bursts of activity in the past, leaving behind gamma-ray bubbles and X-ray echoes in surrounding gas. Dormancy does not mean death. It means a temporary lack of fuel. If a significant inflow of gas were to occur, perhaps from a merger or internal instability, the black hole could ignite again. Whether it would reach quasar luminosity depends on the available fuel and the structure of the galaxy at that time. The possibility of cyclical quasar activity raises intriguing questions. Do galaxies experience multiple quasar episodes? Observations suggest that many galaxies show traces of past activity: fossil outflows, relic radio lobes, shock fronts, or ionized gas structures. These features indicate that quasar activity may come in bursts rather than a single continuous event. Each burst could last millions of years, separated by long dormant intervals. Over a galaxy's lifetime, it may host several quasar phases, each shaping its evolution in distinct ways. Although the exact frequency of these cycles is uncertain, the concept of episodic quasar feedback is widely accepted. Another important aspect of the quasar life cycle is the coevolution of the black hole and its host galaxy. Observations show a strong correlation between black hole mass and the stellar mass of the galaxy's bulge. While the cause of this correlation is debated, its existence implies that galaxies and black holes grow together. During a quasar's peak phase, star formation often reaches its own maximum, fueled by the same gas inflows that feed the black hole. Yet as the quasar intensifies, its feedback may suppress further star formation, especially in the central regions. This interplay suggests that the quasar both participates in and regulates galaxy growth. Whether the quasar is the primary regulator or merely one part of a larger system controlled by the dark matter halo is still uncertain, but the connection between the black hole and its host galaxy is one of the defining features of modern astrophysics. As quasars decline, their host galaxies evolve into more familiar structures. Star formation slows, gas content decreases, the galaxy becomes more stable, often forming a bulge and disk. The central black hole remains as a remnant of the quasar era, but its influence becomes gravitational rather than luminous. Over billions of years, the galaxy may undergo additional mergers, potentially triggering new inflows of gas and reigniting the quasar. This cyclical nature helps explain why black hole mass correlates with galaxy mass. Both grow during the same episodes of intense activity. The end of a quasar's life is not the end of its influence. The metals produced during starbursts and the gas redistributed by quasar winds contribute to the evolution of future generations of stars. The cavities carved by jets alter the cooling of gas in galaxy clusters. The heated halo gas affects the accretion of intergalactic matter. The quasar's imprint is woven into the galaxy's future. Long after its light fades, even the dormant black hole continues to shape stellar orbits and dynamics. If two galaxies merge, their central black holes may eventually coalesce, producing gravitational waves detectable by future observatories such as LISA. These mergers contribute to the population of supermassive black holes and influence the growth of galaxies. On cosmic scales, the quasar life cycle corresponds to the universe's transition from chaotic infancy to structured maturity. Quasars peak during the era known as cosmic noon, when star formation and galaxy growth were at their highest. After this period, quasar numbers decline as galaxies exhaust their gas supplies or become more stable. This decline reflects the universe's gradual shift from rapid assembly to gradual evolution. The history of quasars is therefore a history of cosmic transformation. By understanding when quasars appear, how long they last, and how they fade, scientists can piece together the broader story of how galaxies form and evolve. Even within their life cycle, quasars remain unpredictable. Some are extremely short-lived, shining for perhaps 1 million years or less. Others may persist for tens of millions of years. Some ignite violently after major mergers, while others flicker gently due to internal instabilities. Some launch powerful jets, others remain radio quiet. Some create massive outflows, others maintain steady accretion. This diversity reflects the range of galactic environments, fuel supplies, and black hole properties. The life cycle of a quasar is not a single path, but a family of paths, each shaped by conditions unique to its galaxy. The next frontier in understanding quasar life cycles will be driven by time-domain surveys that monitor quasars across years or decades. These programs reveal variability patterns, changing look transitions, and rapid fluctuations that hint at the underlying physics of accretion. Upcoming telescopes like the Vera-Rubin Observatory's LSST will witness quasar evolution in real time, capturing transitions that previous generations could only infer. These observations will test models of accretion stability, disk structure, and fueling cycles. The life cycle of a quasar is ultimately a reflection of the universe's capacity for extremes. It begins with vast inflows of gas, reaches peak luminosity that challenges imagination, and fades into a dormant state that can last longer than human history by many orders of magnitude. It is a cycle written across millions of years, shaped by physics both understood and mysterious. And through this cycle, we learn not just how black holes grow, but how the universe itself evolves. And yet, the life cycle is only one part of the story. To fully grasp the role of quasars in cosmic evolution, we must explore their diversity, the many types, categories, observational classes, and strange outliers that refuse to fit neatly into any one description. Quasars may seem like a single class of cosmic object, blindingly bright, distant, and powered by supermassive black holes. But the deeper astronomers look, the more diversity they find. What once appeared to be a simple category has fractured into a spectrum of types, each shaped by different physical conditions, viewing angles, feeding mechanisms, and evolutionary histories. This diversity is not chaos. It is the result of the same underlying physics manifesting differently in systems with different environments. But it also reveals that quasars are far from uniform. They vary in luminosity, radio output, obscuration, emission line structure, accretion rate, jet strength, variability, and host galaxy properties. Some quasars are blazing point-like sources, others are faint, obscured, or hidden behind thick dust. Some launch colossal jets, others do not. Some reside in massive elliptical galaxies, others appear in compact or irregular systems. Understanding this diversity is essential because it reveals not just how quasars behave, but why they behave differently, and what these differences teach us about black hole physics and galaxy evolution. One of the most fundamental distinctions in quasar diversity is between radio-loud and radio-quiet quasars. Roughly 10% of quasars are radio-loud, meaning they emit strong radio waves produced by relativistic jets that extend far beyond the host galaxy. These jets inflate radio lobes, generate synchrotron radiation, and imprint themselves on the intergalactic medium. The existence of radio-loud quasars is unambiguous, supported by decades of radio surveys and high-resolution imaging. But the mystery lies in why only a minority of quasars produce such powerful jets. The leading hypothesis is that black hole spin plays a central role. In the Blandford-Znajek mechanism, a rapidly spinning black hole threaded by strong magnetic fields can channel rotational energy into jets. Simulations support this idea, but direct observational proof remains difficult. Another possibility is that the structure of the magnetic fields near the black hole determines whether jets form. The presence of a magnetically arrested disk, a state in which magnetic flux builds up until it chokes the accretion flow, has been proposed as a trigger for powerful jet formation. This too remains plausible, but not definitively proven. What is certain is that radio-loud quasars are fundamentally different in their impact on their environments. Their jets can heat gas in galaxy clusters, regulate intra-cluster cooling flows, and shape large-scale structure in ways radio-quiet quasars cannot. The distinction between radio-loud and radio-quiet quasars is therefore one of the clearest markers of diversity in quasar populations, revealing differences in both physics and cosmic influence. Another major axis of diversity is obscuration. Some quasars are unobscured, shining clearly in optical and ultraviolet wavelengths. These are often called Type 1 quasars and feature broad emission lines from fast-moving gas near the black hole. Others, known as Type 2 quasars, are obscured by thick layers of dust and gas, hiding their central engines from direct view. In these systems, the broadline region is not visible along our line of sight, but narrow emission lines still reveal the presence of an active black hole. The unified model of active galactic nuclei proposes that this difference largely arises from orientation. If we view the quasar face-on, we see the broadline region. If we view it edge-on, the dusty torus blocks our view. There is strong evidence for this model, including polarized light revealing hidden broad lines in some Type 2 quasars. However, orientation cannot explain all obscured quasars. In some cases, the obscuration is not simply geometric, but evolutionary. Young quasars may be embedded in thick cocoons of dust, created by merger-driven starbursts. As feedback clears the dust, the quasar transitions from heavily obscured to unobscured. This evolutionary sequence is supported by infrared observations showing that some of the most luminous quasars are hidden behind tremendous dust columns. Orientation and evolution together create a rich diversity of obscured and unobscured quasars, each representing a different stage or viewpoint of quasar life. Beyond radio properties and obscuration, quasars also vary in their emission line characteristics. Some quasars exhibit extremely broad emission lines, indicating gas moving at tens of thousands of kilometers per second. Others show unusually narrow broad lines, or even a lack of typical broad lines. A subclass known as narrow-line safe-at-one galaxies, NLS-1s, contains black holes with relatively low masses but high accretion rates. These galaxies often show rapid variability, strong Fe2 emission, and occasionally launch jets despite their lower masses. The existence of NLS-1s challenges the simplistic notion that only massive black holes can power powerful active nuclei. Another subclass known as broad absorption line, BAL quasars, features deep absorption troughs in their spectra caused by high-speed winds. These winds can reach velocities of up to 20% the speed of light, stripping material from the accretion disk and launching it into the galaxy. BAL quasars represent a unique and well-observed population, but the cause of BAL features remains debated. Are BAL quasars simply normal quasars viewed at angles where winds intersect our line of sight? Or are they quasars undergoing a specific evolutionary phase involving intense outflows? Both possibilities have supporting evidence, and the debate remains open. In the realm of extreme quasars, one finds hyperluminous quasars, objects so bright that they push the limits of known accretion physics. These quasars emit more than 100 trillion times the luminosity of the Sun. Some appear to accrete near or beyond the Eddington limit, and their extreme brightness challenges simple models of accretion efficiency. Observations show that these quasars inhabit massive dark matter halos and often reside in overdense regions, suggesting that environmental conditions play a significant role in their formation. Some of these hyperluminous quasars reveal enormous ionization zones stretching across millions of light years, indicating that their radiation shapes vast volumes of intergalactic space. While their luminosities are firmly measured, the exact physics behind their extreme accretion rates remains uncertain. Variability adds another layer to quasar diversity. Most quasars vary in brightness over months to years, but some vary dramatically over days or even hours. Rapid variability suggests small emission regions, sometimes only a few light hours across. This variability can come from instabilities in the accretion disk, fluctuations in the corona, or microlensing events caused by stars in intervening galaxies. In microlensing scenarios, gravitational lensing temporarily magnifies parts of the accretion disk, revealing its structure at microarc-second scales. These observations provide one of the few direct probes of the innermost regions near the black hole. They are well-documented phenomena, supported by multiple lensing systems. However, the interpretation of variability remains complex and sometimes ambiguous. More dramatic than ordinary variability are the changing look quasars, which transform between types over short time scales. A quasar may show broad lines one year and lose them the next, or brighten by a factor of 10 and then fade just as rapidly. These changes are too fast to be explained by long-term accretion evolution, suggesting rapid changes in disk structure or sudden obscuration events. Changing look quasars overturn the assumption that quasar classes are stable. Instead, they show that quasars can jump between observational categories, blurring the lines between types and challenging unified models. This discovery is recent and remains an active field of research. While the existence of these transitions is well established, the underlying causes remain uncertain. Quasars also differ by their host galaxies. Some reside in massive elliptical galaxies with old stellar populations, while others inhabit disk galaxies or merging systems. Infrared and optical imaging reveal that many luminous quasars live in galaxies that have undergone recent mergers or interactions. However, an increasing number of quasars are found in disk-dominated galaxies with no signs of disturbance. This diversity suggests that multiple pathways lead to quasar activation. Environment, gas supply, and internal galaxy dynamics all play roles. Host galaxy diversity also helps explain why some quasars grow rapidly, while others remain faint. A gas-rich merger can feed a black hole intensely, while a quiet disk galaxy may provide only modest accretion. Even the large-scale structure surrounding quasars varies. Some live in dense clusters, while others lie in isolation along cosmic filaments. Studies show that quasars reside preferentially in dark matter halos of specific mass ranges, but the exact relationship between halo mass and quasar activity is still being refined. Some hyperluminous quasars appear in protoclusters, dense regions destined to become massive galaxy clusters. These environments may encourage rapid black hole growth through abundant gas inflows. The connection between quasars and their large-scale environment remains a developing field, with ongoing surveys mapping quasar clustering and halo occupation. At the extreme edge of diversity lie the rarest quasars, objects that defy classification. Some quasars show unusually weak emission lines, known as weak-line quasars. Others are heavily reddened by dust, appearing almost invisible in optical light but blazing in infrared. A few exhibit spectral features unlike any known category, possibly due to unusual gas conditions or extreme accretion states. There are quasars that turn off almost completely, leaving faint remnants. There are quasars with double-peaked emission lines, suggestive of massive disks or binary black holes. There are quasars whose spectral features appear offset, hinting at recoiling black holes kicked by gravitational waves, an exciting but not yet confirmed possibility. These outlier quasars test the limits of astrophysical models and represent fertile ground for discovering new physics. Diversity also arises from cosmic time. Quasars in the early universe differ fundamentally from quasars today. Early quasars are more luminous, more massive, and inhabit more chaotic environments. They appear to accrete more efficiently and form more rapidly. Their host galaxies are compact and gas-rich, undergoing intense star formation. In contrast, quasars in the modern universe are less extreme, feeding on smaller gas supplies and living in more stable galaxies. This temporal diversity reflects the overall decline in cosmic gas density and the evolution of galaxy structure. Despite the immense variation among quasars, unifying patterns exist. Their diversity can be understood as the product of a small set of physical parameters: black hole mass, accretion rate, spin, magnetic field strength, orientation, and environment. By adjusting these parameters, one can produce the full spectrum of observed quasar behavior. However, the exact mapping between these parameters and observed properties remains complex. This complexity is why quasar classification continues to evolve. What began as a simple distinction, radio quasars versus optical quasars, has expanded into a multi-dimensional space of possibilities. As scientific understanding deepens, the diversity of quasars becomes not a complication but a clue. It reveals the breadth of environments in which black holes grow, the range of accretion states possible, and the interplay between orientation and intrinsic differences. It shows that quasars are not static entities but dynamic participants in the cosmic ecosystem. Their variations reflect differences in feeding, structure, obscuration, age, and cosmic context. To understand quasars fully, one must observe them not just through a single telescope or a single type of light, but through the entire electromagnetic spectrum. Quasars are multi-wavelength objects whose true nature is revealed only when radio, infrared, optical, ultraviolet, X-ray, and gamma-ray observations are synthesized into one coherent picture. Each wavelength acts like a different diagnostic tool, exposing a different physical process occurring near the black hole. Radio waves trace jets and lobes. Infrared reveals dust and obscured regions. Optical light unveils broad emission lines and accretion disk structure. Ultraviolet reveals ionized winds. X-rays map the corona and inner disk, and gamma rays track the most energetic processes in the universe. No single wavelength can explain a quasar. Only the combined view exposes its anatomy and behavior. This multi-wavelength approach has been central to quasar science since the moment of their discovery, and it continues to evolve as telescopes grow more powerful and computational techniques reveal structures previously hidden in noise. The discovery of quasars began in the radio era. In the mid-20th century, radio astronomers identified numerous bright radio sources that did not correspond to known stars or galaxies. When optical astronomers attempted to match these radio sources to visible objects, they found faint, star-like points. Spectroscopic analysis unveiled emission lines shifted dramatically toward the red. This revelation that these compact objects lay at cosmological distances was the breakthrough moment. Radio surveys such as the Third Cambridge Catalogue of Radio Sources 3C were responsible for the first known quasars. But this method, while pioneering, revealed only a small fraction of the quasar population. Most quasars are radio quiet and went unnoticed in early surveys. Thus, while radio telescopes opened the door to quasar astronomy, optical and infrared telescopes revealed the true scale of the population. Optical surveys soon expanded the census dramatically. Large-scale sky surveys such as the Sloan Digital Sky Survey, SDSS, revolutionized quasar discovery by collecting optical spectra for millions of objects. SDSS unveiled more than 500,000 quasars, revealing structures in the distribution of redshifts, luminosities, and emission line properties. The characteristic broad emission lines, hydrogen-Balmer series, magnesium, carbon, oxygen, became defining fingerprints of quasars in optical wavelengths. These lines indicated gas moving at thousands of kilometers per second, confirming the presence of supermassive black holes. The optical window also revealed color signatures that allowed astronomers to identify quasars photometrically, even before acquiring spectra. Quasars tend to exhibit power law continua that differ from stellar spectra, allowing algorithms to distinguish them efficiently. The optical range became the primary hunting ground for quasars, but it was limited by dust. Obscured quasars, shrouded in dust near their galactic nuclei, became invisible in optical light, hiding a significant portion of the quasar population. Infrared observations broke that barrier. Dust absorbs ultraviolet and optical light, but re-radiates it in the infrared. Infrared telescopes such as Spitzer, WISE, JWST, and ground-based instruments revealed quasars that optical surveys missed entirely. These obscured quasars often represent earlier or more heavily fueled phases of black hole growth. Their heavy dust content suggests that they may be young quasars emerging from gas-rich mergers or compact, intensely star-forming galaxies. Infrared color selection became a major technique for identifying quasars at high redshift, especially those obscured by dust in their host galaxies. WISE, in particular, uncovered millions of candidate quasars across the sky, dramatically expanding the known population. JWST has now begun to detect quasars at redshifts beyond 7, revealing black holes that existed only a few 100 million years after the Big Bang. These discoveries push models of black hole formation to their limits, forcing scientists to reconsider the pathways that create supermassive black holes so early. Ultraviolet observations reveal another essential layer of quasar physics: winds and outflows. Many quasars exhibit prominent ultraviolet absorption lines caused by gas accelerated outward at thousands of kilometers per second. These broad absorption lines, especially in high ionization transitions such as CIV and SIFE, reveal powerful winds driven by radiation from the accretion disk. Ultraviolet spectroscopy, performed by space-based observatories such as the Hubble Space Telescope, exposes the geometry, velocity, and ionization structure of these winds. It also reveals the intergalactic medium, as quasar light is absorbed by hydrogen clouds along the line of sight. The resulting absorption patterns form the Lyman alpha forest, a critical tool for studying large-scale structure. This ultraviolet forest is one of the strongest observational pillars in modern cosmology. It maps density fluctuations, provides constraints on dark matter models, and reveals the thermal history of the intergalactic medium. The ultraviolet window, therefore, contributes not only to quasar science, but to the broader understanding of cosmic evolution. X-ray observations probe yet another domain: the corona, the innermost regions of the accretion disk, and the base of jets. Quasars emit copious amounts of X-rays, produced when ultraviolet photons from the disk are upscattered by high-energy electrons in the corona. This process, known as inverse Compton scattering, generates X-ray continua that reveal the temperature and structure of the corona. X-ray spectra also show features such as the iron K-alpha line, which is broadened and skewed by relativistic effects near the black hole. These features offer some of the most direct tests of general relativity in the strong gravity regime. Observatories such as Chandra, XMM Newton, NuSTAR, and eROSITA have imaged quasar jets, measured variability in X-ray flux, and mapped shock fronts created by quasar-driven winds. X-ray variability often originates from regions only a few gravitational radii across, revealing the dynamic behavior of plasma near the event horizon. X-ray surveys also uncover hidden quasars buried behind dust that absorbs optical and ultraviolet light but allows X-rays to pass. This makes X-ray astronomy an essential component of quasar identification and classification, especially for obscured populations. Gamma-ray observations capture the most extreme processes in quasars, especially in jet-dominated systems such as blazars. Blazars are quasars whose jets point almost directly at Earth. Relativistic beaming amplifies their brightness, making them some of the brightest gamma-ray sources in the sky. Instruments like the Fermi Gamma-Ray Space Telescope detect flares where gamma-ray output can vary dramatically on timescales of hours. These rapid variations imply that the emitting region is extremely compact, yet capable of accelerating particles to energies far beyond those reached in terrestrial accelerators. Gamma-ray astronomy reveals the violent particle acceleration processes occurring within jets, providing clues to magnetic reconnection, shock acceleration, and turbulence. These observations confirm that quasars are not only luminous but among the most powerful particle accelerators in the universe. The multi-wavelength approach also refines quasar classification. Traditionally, quasars were divided into radio loud and radio quiet, obscured and unobscured, broad line and narrow line. But modern astronomy uses sophisticated spectral energy distributions, SEDs, that combine ultraviolet, optical, infrared, and X-ray data to reveal physical properties. SED fitting can estimate accretion rate, dust content, black hole mass, and star formation rate in the host galaxy. Machine learning models trained on multi-wavelength data can classify quasars with remarkable accuracy, uncovering subtle patterns that traditional methods miss. These approaches highlight the continuum of quasar behavior rather than rigid categories. For example, radio loudness is not binary, it spans a wide range. Obscuration is not simply orientation, it involves dust geometry, evolution, and host galaxy structure. Even the distinction between quasars and lower luminosity, active galactic nuclei blurs when considering the full range of SEDs. Time domain astronomy adds yet another dimension. Multi-wavelength monitoring campaigns observe quasars simultaneously in optical, infrared, and X-ray bands, revealing correlated variability that exposes the coupling between different emission regions. A flare in the corona may cause a delayed response in the accretion disk, allowing astronomers to map the geometry using reverberation mapping. This technique, which measures the time delay between continuum and line emission, reveals the size and structure of the broadline region. It is one of the most powerful tools in black hole mass estimation. Time domain surveys, such as the Vera Rubin Observatory's LSST, will capture quasar light curves for millions of objects, enabling studies of flickering, transitions, and rare events never before seen. Quasar discovery also expands through gravitational lensing. When a massive galaxy lies between Earth and a quasar, its gravity bends the quasar's light, producing multiple images, or arcs. Lensed quasars magnify the quasar's inner structure, allowing astronomers to study microlensing effects that expose accretion, disk sizes at unprecedented resolution. Lensing also provides constraints on the distribution of dark matter in the lensing galaxy. Time delays between multiple lensed images allow measurements of cosmological parameters, independent of other distance indicators. Lensed quasars thus combine astrophysics and cosmology in one unified observational tool. Even at radio wavelengths alone, quasar diversity is extraordinary. Very long baseline interferometry, VLBI, can resolve jets at millisecond scales, revealing knots of plasma moving at apparent superluminal speeds, a relativistic illusion caused by jets moving nearly at the speed of light. These observations show that jets are not continuous beams, but clumpy structures shaped by shocks and magnetic instabilities. VLBI has also imaged the bases of jets near event horizons, showing that jet launching begins extremely close to the black hole. These discoveries strengthen the connection between jet power and black hole spin, though direct measurement of spin remains challenging and model-dependent. As multi-wavelength observations expand, so does the catalogue of unusual quasars. Some quasars appear X-ray weak, emitting far fewer X-rays than expected. Others are hot dust poor, lacking the infrared emission typical of dusty Tauri. A few quasars exhibit periodic brightness modulations that may indicate binary supermassive black holes orbiting each other, a tantalizing but not yet confirmed idea. There are quasars with strange spectral inversions, quasars with nearly featureless continua, and quasars with extremely red colors from heavy obscuration. Each unusual quasar becomes a clue to new physical processes or extreme environments. Some reveal conditions in the early universe, others reveal rare accretion states, and still others may signal the presence of exotic phenomena such as gravitational recoil or evolving magnetic fields. The multi-wavelength nature of quasar research also highlights the limitations of any single observing method. Optical surveys can miss dust-obscured quasars. Infrared surveys can confuse quasars with starburst galaxies. X-ray surveys may miss objects heavily obscured by gas. Radio surveys find only the jet-producing minority. Gamma-ray surveys detect only blazars. Only by combining all these windows does the full diversity of quasars become clear. Modern quasar science is therefore inherently interdisciplinary, blending observational astronomy, high-energy astrophysics, computational modeling, spectroscopy, machine learning, and cosmology. The picture that emerges from multi-wavelength studies is one of profound unity hidden beneath enormous diversity. Quasars look different depending on orientation, dust content, jet strength, accretion rate, black hole mass, and host galaxy environment, but the underlying engine, a supermassive black hole fed by an accretion disk, remains the same. The diversity reveals not noise but structure, not chaos but complexity guided by physics. Quasars do not simply inhabit the universe, they interact with it, influence it, and in many ways illuminate its very architecture. They are beacons scattered across the cosmic landscape, some so distant that their light predates entire generations of stars in our own galaxy. When astronomers talk about the large-scale structure of the universe, the cosmic web of dark matter, gas filaments, voids, galaxy clusters, protoclusters, and superclusters, quasars become essential tools for mapping and understanding these colossal forms. Their extreme luminosity allows them to be seen across vast distances, often serving as the only visible lighthouses piercing the early fog of cosmic evolution. But quasars are not merely markers, they are participants. Their energy output shapes the thermal history of the intergalactic medium. Their feedback influences gas flows on megaparsec scales, and their clustering reveals the distribution of dark matter halos across cosmic time. To understand the universe's largest structures, one must understand the role quasars play within them. The story begins with dark matter, the invisible scaffolding that shapes the cosmic web. Galaxies do not form randomly in space. They form within dark matter halos, gravitational wells where gas can cool, condense, and collapse into stars. Quasars are found in particularly massive halos, reflecting their need for abundant gas supplies. These halos sit at the intersections of filaments, where flows of gas converge. This means quasars often reside in special locations, cosmic crossroads, where material is funneled inward along the web. Observations using galaxy clustering and quasar correlation functions show that quasars occupy dark matter halos with masses around 1 trillion solar masses, although the exact value varies with redshift and luminosity. This correlation between quasar positions and halo mass is one of the strongest pieces of evidence that quasars trace the underlying structure of the universe. It also reveals that quasars are excellent probes of dark matter distribution, even though they themselves contain no dark matter in their central engines. Quasar clustering provides insight into the growth of large-scale structure. By measuring how quasars are distributed relative to each other, astronomers can infer the mass of the halos they occupy and the cosmological parameters governing cosmic expansion. Surveys such as SDSS, DESI, and EBOS have produced detailed maps of quasar, clustering across billions of light years, demonstrating that quasars are not randomly placed but follow the shape of the cosmic web. These clustering measurements reveal the imprint of baryon acoustic oscillations, sound waves left over from the early universe, preserved in the large-scale distribution of matter. Quasars, by virtue of their brightness, extend these measurements to higher redshifts than galaxies alone can reach. In this sense, quasars act like cosmic rulers, helping calibrate the expansion history of the universe. Quasars also influence the intergalactic medium, shaping its temperature and ionization state. Their ultraviolet and X-ray radiation can travel tens or hundreds of millions of light years, creating ionized bubbles around them. In the early universe, these bubbles played a role in ionizing helium, an event that occurred roughly 3 billion years after the Big Bang. While stars were the primary drivers of hydrogen ionization, quasars contributed significantly to heating and ionizing helium, marking a distinct phase in cosmic history. This helium ionization phase left thermal signatures in the intergalactic medium that can be measured today through Lyman alpha forest observations. These signatures reveal temperature changes linked to quasar activity, showing that quasars influenced cosmic gas far beyond their host galaxies. In addition to reionization, quasars contribute to the heating of cosmic filaments and galaxy clusters. Their jets and winds inject energy into gas residing outside galaxies, altering its temperature and preventing it from cooling effectively. This heating helps regulate the gas supply available for future galaxy formation. In galaxy clusters, quasar-driven jets inflate enormous cavities visible in X-ray maps as ghostly bubbles. These cavities represent mechanical work done by the black hole on the surrounding medium, evidence of direct interaction between a tiny central engine and a galactic-scale environment. Clusters containing radio-loud quasars often show reduced cooling flows, reinforcing the idea that quasar feedback prevents runaway gas collapse. These interactions are well-established phenomena supported by decades of X-ray and radio observations. Quasars serve not only as influencers, but also as backlights. Their bright spectra allow astronomers to detect absorption features caused by gas in the intergalactic medium. The Lyman Alpha Forest is the most famous example. Each absorption line corresponds to a cloud of hydrogen along the line of sight, providing a detailed map of cosmic gas distribution. But quasars reveal more than hydrogen. They expose metals in the intergalactic medium: carbon, silicon, oxygen, tracing the spread of elements created by early generations of stars. They reveal the density and temperature of the cosmic web. They reveal the presence of proto-galaxies too faint to detect directly. Through quasar absorption line studies, astronomers reconstruct the invisible threads that connect galaxies across vast distances. Without quasars, this structure would remain largely hidden. Beyond the intergalactic medium, quasars act as probes of the circumgalactic medium, the halo of gas surrounding individual galaxies. This gas reservoir plays a crucial role in galaxy evolution, providing fuel for star formation and acting as an interface between galaxies and the cosmic web. Quasars located behind other galaxies shine through the circumgalactic medium, their light revealing gas flows, ionization states, and metal content. These absorption line studies show that galactic halos are dynamic environments shaped by inflows from the cosmic web and outflows driven by star formation and quasar activity. This interplay between inflow and outflow is central to galaxy evolution, and quasars provide a window into this complex gas cycle. On even larger scales, quasars illuminate protoclusters, the ancestors of modern galaxy clusters. Protoclusters are regions of the early universe where galaxies and dark matter halos assemble rapidly. Quasars often appear in these dense environments, where abundant gas supplies fuel rapid black hole growth. Observations with JWST and ALMA have revealed quasars surrounded by overdensities of galaxies, suggesting that their hosts reside in early cluster-forming regions. These environments are chaotic, starburst-rich and gas-dense, providing ideal conditions for quasar ignition. Studying quasars in protoclusters offers a view of structure formation in its most dramatic and formative stages. Quasars also help define the cosmic star formation history. Their number density across redshift peaks around the same time as the universe's global star formation rate, about 10 billion years ago. This coincidence suggests a connection. The same gas that fuels star formation also fuels black hole growth. As galaxies mature and gas supplies diminish, both star formation and quasar activity decline. This parallel evolution is supported by observational data across multiple surveys. Quasars, therefore, serve as markers of the universe's transition from a gas-rich, star-bursting era to a calmer, more structured phase dominated by mature galaxies. Yet perhaps the most profound way quasars shape large-scale evolution is through feedback. Their outflows, jets, and radiation do not remain confined to their host galaxies. They escape into the intergalactic medium, pushing, heating, and stirring material across enormous distances. Simulations show that quasar-driven winds can influence the metallicity of the intergalactic medium, the temperature of cosmic filaments, and the cooling of gas in galaxy groups. These interactions reveal quasars as engines of environmental change, capable of altering the cosmic landscape. Despite this immense influence, many questions remain unsettled. How far do quasar winds actually propagate? How efficiently do they transfer energy into the intergalactic medium? How do different quasar types influence their environments? How do jets and winds interact with cosmic filaments? While simulations provide plausible answers, the details remain uncertain, and upcoming observatories are expected to refine these models significantly. One especially intriguing frontier involves using quasars as tools for precision cosmology. Because quasars are observed across a vast range of redshifts, they provide a unique opportunity to measure cosmic expansion over time. While they are not standard candles in the traditional sense, new techniques repurpose quasars as distance indicators through their variability, emission line properties, or accretion disk size estimates. These methods are still in development and not yet part of the scientific consensus, but they hold potential for independent checks on the Hubble constant and the nature of dark energy. If refined quasar-based cosmological measurements could help resolve tensions between early universe and late universe expansion rates. Gravitational lensing of quasars adds another layer to cosmology. Time delays between multiple lensed images allow precise measurements of cosmological distances. These time delay lenses form the basis of the H0LiKW project, which uses lensed quasars to measure the Hubble constant independently of other techniques. This method has already produced competitive results and is expected to grow more powerful as more lensed quasars are discovered. In this way, quasars become tools not just for astrophysics, but for probing the fundamental parameters of the universe. Even the distribution of quasars across redshift provides insights into cosmic evolution. The sharp rise and fall of quasar populations reflect changes in gas availability, galaxy merger rates, and halo growth. Their disappearance at later times reveals the universe's transition to a low accretion state. Their early abundance hints at rapid black hole growth in the aftermath of the first stars. Each redshift slice offers clues about the conditions of the universe at that era. Quasars also play a role in exploring the physics of the cosmic web itself. Their absorption lines trace density fluctuations on small and intermediate scales, allowing comparisons with predictions from dark matter simulations. These comparisons test cosmological models, including warm dark matter scenarios, fuzzy dark matter hypotheses, and alternative gravity models. While the consensus strongly favors cold dark matter, quasars provide one of the few tools capable of distinguishing between different dark matter particle properties. Looking into the future, the role of quasars in large-scale cosmology will only grow. Upcoming surveys will map millions of quasars across the sky, producing detailed three-dimensional maps of the universe extending to unprecedented distances. These maps will reveal the evolution of structure across almost the entire history of the cosmos. They will also refine measurements of dark energy, dark matter, and cosmic geometry. In this way, quasars are not merely astronomical objects. They are cosmic instruments encoded with the universe's history. Their presence reveals where dark matter halos formed. Their light maps the cosmic web. Their clustering measures expansion. Their absorption traces the intergalactic medium. Their feedback shapes galaxy evolution. Their brightness illuminates the early universe. Their rarity in the present era signals cosmic aging. Each quasar is both a participant in and a witness to the universe's evolution. A quasar is more than a luminous object. It is a laboratory for the most extreme physics known to exist. A natural particle accelerator, a relativistic engine, a magnetic crucible, and a region where the laws of physics bend, stretch, and reveal their deepest workings. If you want to test general relativity in the strong gravity regime, you look near the event horizon of a quasar. If you want to understand plasma dynamics at relativistic speeds, you study its jets. If you want to probe the behavior of magnetic fields under conditions impossible to recreate on Earth, you turn to its accretion disk. And if you wish to explore whether fundamental constants have remained unchanged since the early universe, you analyze quasar absorption lines. Quasars sit at the frontier of physical knowledge, acting as cosmic laboratories where nature conducts experiments far beyond human capability. Yet despite this extraordinary scientific value, Quasars also expose cracks in our understanding of physics, places where theories break down, where predictions fail, and where observations diverge from expectations. By studying quasars, we are not merely observing distant objects, we are testing the foundations of reality itself. Near the event horizon, the warping of spacetime becomes so severe that classical intuition collapses. Matter does not follow straight paths, but spirals along geodesics distorted by curvature. Photons are bent, redshifted, and trapped. Time slows relative to observers farther away. Accreting material forms, structures that are both familiar in shape, yet fundamentally shaped by relativistic forces. General relativity predicts the behavior of such environments with startling accuracy, but only up to a point. Observing quasars allows scientists to test these predictions directly. For example, the broad iron K-alpha emission line, one of the most important features in X-ray spectra, emerges from a region mere gravitational radii from the event horizon. Its asymmetric, skewed shape results from Doppler boosting, gravitational redshift, and light-bending effects predicted by relativity. When telescopes measure these features, they confirm the theory's predictions. However, measurements also reveal complexities, variability in line shape, unexpected changes in the corona, and fluctuations in disk thickness that require refinements to existing models. These discrepancies are not failures of relativity, but reminders that real astrophysical environments are far more complex than simplified textbooks suggest. The corona above the accretion disk is itself a mystery. It is a region of extremely hot plasma, with electrons accelerated to energies that upscatter ultraviolet photons into X-rays. Yet the corona's structure remains uncertain. Some models propose a compact lamppost corona hovering just above the black hole. Others propose an extended patchy corona covering much of the disk. Reverberation mapping, measuring the time delay between X-ray flares in the corona and their reflections off the disk, provides clues. These delays reveal distances measured in light hours, allowing astronomers to map corona geometry indirectly. Observations consistently show that the corona can contract and expand over short timescales, implying dynamic magnetic processes. Some models suggest magnetic reconnection as the primary heating mechanism, similar to solar flares, but vastly more powerful. Others propose turbulence-driven dissipation. The truth remains unsettled. What is certain is that the corona is unstable, dynamic, and intimately tied to the processes that produce jets and winds. Jets themselves provide one of the most dramatic examples of extreme physics. They accelerate particles to energies far beyond what human-made accelerators can achieve and maintain coherence across scales millions of times larger than their launch regions. Observations reveal knots of plasma traveling with apparent superluminal velocities, an illusion created by relativistic beaming as the jet moves close to the speed of light. The mechanisms that launch and sustain these jets remain one of the great unsolved challenges of astrophysics. The Blandford-Znajek process, which extracts rotational energy from a spinning black hole through magnetic fields, is a leading explanation. But the details, how magnetic flux accumulates, how fields remain organized, how plasma is collimated, are still active research areas. Numerical simulations have advanced dramatically, yet even they struggle to capture the full complexity of relativistic magnetohydrodynamics near the event horizon. These simulations suggest that jets originate when magnetic fields become so strong they arrest the inflow of gas, forming a magnetically arrested disk. This scenario is promising, but not definitively proven. As technology improves, observatories like the Event Horizon Telescope may eventually resolve the bases of jets in greater detail, offering direct tests of these theories. The accretion disk also serves as a laboratory for turbulence, viscosity, and angular momentum transport. The magneto-rotational instability, which explains how disks transfer angular momentum outward and allow matter to fall inward, is now widely accepted. Yet its full behavior in radiation-dominated, relativistic environments remains uncertain. Disks may exhibit thermal instabilities, oscillations, and structural changes that current models only approximate. High-frequency, quasi-periodic oscillations observed in some active galactic nuclei may correspond to disk oscillations near the ISCO, offering possible probes of black hole spin. These oscillations, if definitively identified, would provide a direct test of general relativity's predictions about orbital frequencies near black holes. But they remain difficult to interpret because variability arises from multiple competing processes: turbulence, magnetic reconnection, shocks, and radiation pressure instability. On a different front, quasars test the transparency of the universe to high-energy photons. Gamma rays from distant quasars must travel through the cosmic background of photons produced by stars and galaxies. As gamma rays interact with low-energy photons, they can produce electron-positron pairs, limiting their travel. Observing how much gamma-ray flux arrives at Earth allows scientists to infer the density of this cosmic background. These measurements provide constraints on star formation history across cosmic time. Additionally, they test models of photon-axion interactions, an area of speculative physics. Axions are hypothetical particles that might convert into photons in magnetic fields. If such conversions occur, some gamma rays could travel farther than expected. While no conclusive evidence supports axions yet, quasars provide one of the few astrophysical laboratories where such exotic phenomena could be tested. Quasar absorption lines also test the stability of fundamental constants. By comparing the wavelengths of atomic transitions in quasar spectra with laboratory measurements, scientists test whether physical constants, such as the fine structure constant, have changed over billions of years. Some studies have suggested hints of tiny variations, while others find no change. The current consensus is that if variations exist, they're extremely small and not yet confirmed. Quasars, however, remain the only probes capable of reaching such cosmological timescales. Even null results strengthen our understanding by confirming the stability of physics across most of cosmic history. Quasars also test theories beyond general relativity. Some alternative gravity models predict deviations in how accretion disks behave, how jets form, or how light bends near black holes. While no alternative model has matched the predictive success of general relativity, quasars provide strong field environments where deviations might appear. Observational constraints from quasar spectra, timing, and gravitational lensing rule out many exotic models, shaping the landscape of theoretical physics. One of the most promising areas for new physics involving quasars is gravitational wave astronomy. While current gravitational wave detectors focus on mergers of stellar mass black holes and neutron stars, future observatories such as LISA will detect mergers of supermassive black holes. These events, when two massive black holes spiral together, will release enormous energy in gravitational waves and may be associated with bright quasar activity. If electromagnetic signals accompany these mergers, quasars could become part of multi-messenger astronomy, allowing scientists to probe black hole growth, disk dynamics, and the influence of spin. Observing such events would test general relativity in the dynamical strong field regime, complementing static tests like those near the event horizon. Quasars even help probe plasma physics under extreme conditions. Their jets contain relativistic electrons spiraling in magnetic fields, producing synchrotron radiation. The spectral signatures of this radiation reveal magnetic field strengths, particle energy distributions, and shock structures. These processes are relevant not only to quasars, but to pulsars, gamma-ray bursts, and cosmic ray acceleration throughout the universe. Jets test theories of magnetic reconnection, turbulence, and plasma instabilities in ways no laboratory experiment on Earth can replicate. Some features of jets, such as helical magnetic structures and periodic brightening, remain difficult to explain fully, indicating that plasma physics in these environments may involve processes not yet fully understood. On the largest scales, quasars test the distribution of dark matter in cosmic filaments. By analyzing the absorption lines in quasar spectra, astronomers map the distribution of neutral hydrogen and infer the underlying dark matter structure. These observations match simulations of cold dark matter remarkably well, strengthening the case for the standard cosmological model. However, small-scale discrepancies, such as the distribution of small galaxies and the behavior of warm gas, have led some scientists to explore alternative dark matter models. Quasar absorption studies provide constraints on these models by revealing how matter clusters on small scales. While cold dark matter remains the dominant theory, quasars continue to provide essential tests. The nature of the quasar's dusty torus also touches on fundamental physics. Dust grains in the torus experience temperatures, radiation pressures, and sublimation levels far beyond ordinary astrophysical environments. Studying how dust survives, evaporates, and reforms in these extreme conditions improves understanding of grain chemistry, radiative transfer, and the life cycle of dust in galaxies. Infrared interferometry from telescopes like JWST and ALMA has begun to resolve these structures, revealing complex geometries inconsistent with early simplistic torus models. These refined observations test physical models of dust dynamics, radiation pressure equilibrium, and anisotropic emission. Even quasar-host galaxies provide laboratories for physical processes. Starburst activity in these galaxies tests theories of stellar feedback, gas cooling, and chemical enrichment. Massive outflows driven by quasars test hydrodynamic models of galaxy-scale winds. Galaxy mergers hosting dual quasars test the dynamics of black hole pairing and the mechanisms that drive them toward eventual coalescence. All these processes contribute to our understanding of how galaxies and the universe at large evolve. Ultimately, quasars bring together multiple frontiers of physics: relativity, electromagnetism, quantum mechanics, plasma physics, thermodynamics, and cosmology. They expose the seams where theories converge and the cracks where they diverge. They test predictions made decades ago and inspire new theories for the decades ahead. They remind scientists that the universe contains natural experiments far more extreme than anything humans can build. And while quasars teach us about the universe, they also remind us how much remains unknown. Quasars are not just features of the universe. They are milestones in its evolution, markers of transition, catalysts of transformation, and witnesses to epochs that shaped everything that came after. To understand cosmic history is to recognize the profound role quasars played during specific eras, sometimes subtly, sometimes violently. They are among the earliest luminous objects to appear after the first stars and galaxies emerge from cosmic darkness. They influence the distribution of matter, the ionization state of the intergalactic medium, the enrichment of cosmic gas with heavy elements, and the formation of large-scale structures. Their radiation pierced vast regions of space long before galaxies settled into the familiar spiral and elliptical forms we see today. When we examine the timeline of the universe, from the first few 100 million years after the Big Bang to the era of galaxy maturity, we find quasars interwoven into every chapter. Their appearance, peak, and decline reflect the universe's transformation from a hot, dense infant cosmos into a structured tapestry of galaxies, clusters, and cosmic web filaments, and their influence lingers long after the quasar itself fades. The emergence of quasars in the early universe is a profound puzzle and a foundational part of cosmic history. Only A few 100 million years after the Big Bang, the first supermassive black holes had already grown to masses of hundreds of millions, or even billions of suns. This rapid assembly seems almost impossible under standard growth models. Yet observational evidence leaves no room for doubt. Quasars at redshifts above 7 shine bright enough that their light began travelling toward us more than 13 billion years ago. These ancient quasars reveal an era when the universe was dense, gas-rich, and far more chaotic than it is now. Their presence indicates that galaxy formation was already well underway, that gas had begun collapsing into dense regions, and that black holes were capable of reaching extraordinary sizes at super Eddington rates or through massive seed formation. These early quasars are cosmic archaeologists' greatest gifts, revealing how the universe transitioned from primordial simplicity into a realm of complex structures. But quasars did not merely illuminate the early universe, they transformed it. When the first generations of stars formed, they began the long process of reionizing hydrogen, reversing the cosmic fog that had settled after recombination. Quasars joined this process by emitting enormous quantities of ultraviolet and X-ray photons. Though stars contributed most of the ionizing power for hydrogen, quasars played an essential role in ionizing helium. This secondary ionization phase heated the intergalactic medium significantly, leaving temperature signatures that we can still detect in Lyman alpha forest observations. These signatures tell us that quasars were not mere spectators, they were active participants in shaping thermal conditions across millions of light years. The timing, patchiness, and intensity of helium reionization are closely tied to quasar populations. As the number of quasars increased, helium became progressively ionized, and regions of the universe heated dramatically. Moreover, quasars influenced how quickly galaxies enriched themselves with metals. The winds and outflows generated by quasars carried heavy elements into the intergalactic medium, seeding vast regions of space with the products of stellar nucleosynthesis. Observations of absorption lines against quasar spectra reveal metal-enriched gas far from any visible galaxy. The most plausible explanation is that quasar-driven outflows expelled enriched material into the cosmic web. This process helped distribute carbon, silicon, oxygen, and other elements across large-scale structures long before quiet galaxy evolution took over. Without quasars, the universe might have remained chemically patchy for far longer. Stars rely on metals to cool gas efficiently, so quasar-driven enrichment likely accelerated the pace at which future generations of galaxies formed and evolved. The metallicity measured in distant, damped Lyman alpha systems supports this idea, showing evidence of early enrichment that occurred too rapidly to be explained by stars alone. Quasars also played a role in regulating star formation within galaxies. In the early universe, galaxies were small, dense, gas-rich, and prone to runaway star formation. Without some kind of regulating force, many galaxies would have converted all their gas into stars rapidly, leaving them unable to grow steadily. Quasar feedback, through radiation pressure, winds and jets, provided this regulatory force. As black holes accreted material, they released energy capable of heating or removing gas, preventing premature consumption. This helped galaxies grow more gradually, stabilizing their evolution. Observations of massive galaxies in the early universe show signs of suppressed star formation, consistent with quasar-driven quenching. This quenching is not always absolute. Some galaxies continued forming stars even during quasar phases, but the overall effect was to prevent the catastrophic overgrowth predicted by simulations lacking feedback. On larger scales, quasars helped shape the structure of the cosmic web. Their radiation heated regions of the intergalactic medium, altering cooling times for gas and influencing the flows of matter into galaxies. In dense regions where protoclusters were forming, quasars likely contributed to the overall heating of halo gas, preventing certain structures from collapsing too quickly. These processes are visible today as thermal echoes in the Lyman Alpha Forest, where temperature fluctuations reveal past quasar activity. The sizes of proximity zones, regions of ionized hydrogen around quasars, tell us how active black holes shape their surroundings over tens of millions of years. These zones are not merely diagnostic tools. They are fossil indicators of how quasars altered the large-scale structure around them. Quasars also shaped the long-term evolution of galaxy clusters. Their jets created cavities in hot intra-cluster gas, which remain observable for hundreds of millions of years. These cavities show that quasars played a role in regulating cooling flows, preventing massive clusters from forming stars too rapidly at their centers. Quasar jets also transported magnetic fields into the intracluster medium, contributing to the tangled magnetic environment observed today. These effects demonstrate that quasars influence not only individual galaxies, but entire cosmic ecosystems. Quasars played another role in cosmic history. They acted as navigation markers for the universe's growth. By examining their redshift distribution, scientists learn about the rate of galaxy mergers, the availability of cold gas, the formation of dark matter halos, and the timeline of cosmic expansion. The rise and fall of quasar populations correspond to major shifts in cosmic conditions. When gas supplies were plentiful during the universe's first few billion years, quasars flourished. As galaxies matured and gas supplies dwindled, quasar numbers declined. This decline mirrors the drop in cosmic star formation, revealing a linked evolutionary trajectory. Between roughly 2 and 4 billion years after the Big Bang, the quasar population reached its peak, marking a turning point in cosmic history. It was a period of cosmic adolescence when galaxies, black holes, and the intergalactic medium underwent rapid transitions. As the universe aged, quasars became rarer but no less important. Their diminishing numbers reflect changing environmental conditions. Gas became less abundant, dark matter halos grew more stable, and galaxy interactions slowed. Black holes still grew, but not with the ferocity of earlier epochs. Quasar feedback continued to regulate massive galaxies, ensuring they did not reignite in uncontrolled starbursts. By the time the universe reached half its current age, quasar activity had fallen dramatically. Yet even the remnants of quasar outbursts, cavities, enriched gas, relic radiolobes, continued to shape galaxies and clusters. Quasars also left an imprint on the universe through gravitational lensing. Many quasars are positioned behind massive galaxies or clusters, creating multiple images, arcs, or magnified structures. These lensing events help scientists map the distribution of dark matter in the intervening structures. They reveal substructure in halos, test dark matter particle properties, and provide independent estimates of cosmological parameters. In this sense, quasars indirectly advanced our understanding of dark matter and cosmic expansion long after their light first left the host galaxy. In the modern universe, active quasars are far less common. The supermassive black holes that once powered them now sit mostly dormant. But these dormant black holes remain as monuments to cosmic history, silent ruins of luminous epochs long past. Their masses record the integrated history of accretion and mergers. Their host galaxies bear the signatures of their influence. Their surrounding halos hold metals once expelled by their winds. The universe today is shaped not only by what quasars are, but by what they were. Even now, quasars continue to play a critical role in astrophysical research. They remain the brightest persistent sources known, allowing astronomers to look farther into space than with almost any other type of object. They illuminate intervening matter, map cosmic structure, test physical laws, and anchor our understanding of the early universe. Their diversity, luminosity, and vast distances make them ideal probes of cosmic history. In every epoch, from the first billion years to the present, quasars have served as both engines and archives of cosmic evolution. They transformed galaxies, altered gas flows, shaped the cosmic web, drove ionization, distributed elements, and revealed the universe's structure. Their light, traveling across billions of years, carries with it a record of the universe's transformation from primordial chaos to complex order. The story of quasars is far from complete. In fact, despite decades of progress, the field stands on the edge of a profound transformation. The telescopes of yesterday revealed quasars as luminous mysteries. The instruments of today are dissecting them into components. But the observatories and detectors of tomorrow will expose details so fine, so fundamental, and so extreme that our current theories may be forced to evolve. We are entering an era when quasars will not only be observed more deeply, more sharply, and more broadly across the spectrum than ever before. They will be observed in new ways entirely. Their jets will be mapped in real time. Their accretion disks will be spatially resolved. Their environments will be probed with unprecedented sensitivity. Their origins will be tested against the earliest cosmic epochs, and their mergers will be heard through gravitational waves. The future of quasar science is not a continuation of the past, but a revolution driven by technology, computation, and theoretical progress. Just as early radio astronomers could not imagine the richness uncovered by modern optical and X-ray telescopes, we today can only glimpse the magnitude of discoveries ahead. Yet even that glimpse reveals a field poised for breakthroughs that will reshape our understanding of cosmic evolution, black hole physics, and the fundamental forces of nature. The first major driver of this quasar renaissance is a new generation of telescopes that can peer farther and finer than their predecessors. JWST has already demonstrated its transformative power by detecting quasars at redshifts greater than 7, probing epochs just a few 100 million years after the Big Bang. These observations are challenging current models of black hole formation, forcing astronomers to reconsider how massive seeds could have formed so quickly. JWST's infrared sensitivity allows it to penetrate dusty environments that obscure earlier telescopes, revealing the host galaxies of early quasars in unprecedented detail. These galaxies appear smaller, more compact, more dynamically chaotic, and more gas-rich than expected, indicating that quasar ignition in the early universe may have been tied to violent, turbulent gravitational collapse. As JWST continues its deep field programs, we expect to discover even earlier quasars, potentially pushing the record to redshifts beyond 10. Such discoveries would demand a reworking of early cosmic timelines, seed formation theories, and accretion models. No matter what JWST finds, the results will not simply fill gaps in our knowledge, they will alter the shape of the puzzle entirely. Parallel to JWST, the upcoming Nancy Grace Roman Space Telescope will map large swaths of the sky with exquisite detail, capturing thousands of quasars in the early and intermediate universe. Roman sensitivity to gravitational lensing will reveal magnified quasars that would otherwise be invisible, allowing astronomers to study their hosts, measure time delays between lensed images, and refine cosmological parameters. These time delay measurements will provide independent estimates of the Hubble constant, contributing to the resolution, or deepening, of the current tension between early and late universe measurements. Roman will also detect quasar variability across vast timescales, revealing how their fuel supplies fluctuate, how their accretion disks reorganize, and how their structures evolve. On the ground, the Vera Rubin Observatory's LSST will revolutionize time-domain astronomy. Over a decade of continuous monitoring, LSST will capture light curves for millions of quasars, charting their flickers, dips, bursts, and transitions with unprecedented precision. it will detect changing-look quasars in real time, enabling astronomers to observe the factors that trigger these dramatic transitions. It will uncover periodic variations that may signal binary supermassive black holes orbiting each other, possible precursors to gravitational wave mergers detectable by future observatories. LSST will also map quasar clustering across half the sky, producing cosmological measurements far more detailed than any existing dataset. In addition to optical and infrared advances, the radio astronomy landscape is undergoing a transformation. The Square Kilometre Array, SKA, once completed, will be the most sensitive radio telescope ever built. It will detect faint, distant radio quasars that current telescopes cannot see, illuminating the role of jets in the early universe. SKA will map the polarization of quasar jets, revealing magnetic field structures that have remained invisible until now. It will detect relic radio lobes from long-dead quasars, uncovering fossil evidence of past activity cycles. It will conduct precise measurements of neutral hydrogen absorption against bright background quasars, tracing the cold gas content of galaxies across cosmic time. SKA's ability to probe the cosmic dawn, the era when the first stars and black holes formed, will make it a cornerstone of quasar science for decades. X-ray astronomy too is poised for dramatic advances. The upcoming Athena mission will deliver far higher spectral resolution and collecting area than existing X-ray telescopes. It will resolve the innermost regions of the accretion disk, measure relativistic reflection features with unprecedented precision, and trace the geometry of the corona. Athena will detect winds with velocities exceeding a significant fraction of the speed of light, providing insights into how quasar feedback operates in detail. It will reveal how energy is distributed between the disk, corona, and outflows, testing models of radiation pressure-driven winds and magnetic acceleration mechanisms. Alongside Athena, the proposed Lynx mission would offer even finer resolution, enabling detailed imaging of quasar jets, shock fronts, and cavities in galaxy clusters. But perhaps the most transformative tool of all will be gravitational wave astronomy. With the launch of LISA in the 2030s, scientists will be able to detect mergers of massive black holes, events that shape the evolution of quasar hosts and produce enormous bursts of gravitational radiation. If these mergers are accompanied by electromagnetic signals, quasars will become multi-messenger laboratories. LISA will detect in spirals occurring over months or years, allowing astronomers to anticipate merger events and observe them across the spectrum. These observations will test whether quasars light up during black hole pairing, how gas behaves as spacetime shakes violently, and whether kicks from gravitational recoil can displace newly merged black holes. Such phenomena, currently speculative, will become observational science. Simulations are another pillar of the future. As computational power grows, simulations of quasar environments will incorporate more physics. Radiation hydrodynamics, full relativistic magnetohydrodynamics, dust grain evolution, cosmic ray transport, and feedback coupling across scales from the event horizon to the circumgalactic medium. These simulations will no longer be constrained to small patches of the accretion disk. They will model entire quasar systems for millions of years. They will follow gas from cosmic filaments into galaxies, through star-forming regions, through the accretion disk, and finally into jets and winds. They will test theories of seed formation by simulating direct collapse black holes at resolutions never before possible. They will explore how black holes influence galaxy morphology, metallicity, and star formation efficiency, and they will provide theoretical predictions for observatories like JWST, Athena, LISA, and SKA, unifying observation and computation. The future of quasar science also involves expanding our understanding of diversity within the quasar population. As samples grow to millions, rare classes will emerge more clearly. Dual quasars, two supermassive black holes actively accreting within the same galaxy, will be identified in higher numbers. These systems are critical for understanding black hole mergers, but today only a handful are confirmed. With future telescopes, dozens or hundreds may be found, allowing statistical studies. Even rarer phenomena, such as quasars displaying periodic gravitational lensing, extreme microlensing events, or signatures of recoiling black holes, will become more accessible. Outlier quasars with unusual spectra, extreme variability, or peculiar environments will test the boundaries of existing models. Another frontier involves connecting quasar science with dark matter physics. High-resolution absorption studies against quasars may detect subtle deviations from cold dark matter predictions, potentially revealing properties of warm, fuzzy, or self-interacting dark matter models. If such deviations are observed consistently, they could reshape our understanding of cosmic structure. Quasars may also help constrain the nature of dark energy by mapping large-scale structure growth across cosmic time. At the intersection of quasar science and fundamental physics lies the possibility of detecting changes in physical constants over billions of years. Upcoming spectrographs with higher precision will test whether constants like the fine structure constant remain stable across cosmic history. While current evidence shows no confirmed variation, future instruments may detect patterns invisible today. Such a discovery would revolutionize physics, and quasars would be the astronomical laboratories that made it possible. The final piece of the future landscape involves philosophy as much as physics. As we probe quasars more deeply, we confront fundamental questions about the universe. How do black holes grow? Why do galaxies evolve the way they do? What governs the interplay between gravity and radiation? Is general relativity complete, or merely a low-energy approximation of a deeper theory? Quasars push these questions to the breaking point. They expose where our theories succeed and where they falter. They illuminate where new physics might emerge. The next decades will not merely refine our understanding of quasars, they will transform it. New telescopes will expose hidden structures. New simulations will reveal unseen dynamics. New detectors will hear the universe in ways never before possible. And through these advancements, quasars will shift from being objects of awe to objects of deep precision science. From distant beacons to laboratories where the universe allows us to test its most fundamental laws. Quasars are not only astrophysical phenomena, they are philosophical provocations. They force us to confront questions that stretch far beyond astronomy, reaching into our understanding of existence, time, causality, and humanity's place in a universe shaped by forces so vast that our language struggles to contain them. To look at a quasar is to look at a paradox, a region where an object that emits no light gives rise to the brightest illumination in the cosmos. A place where destruction becomes creation. A moment from the distant past appearing vividly in the present. A system governed by deterministic physical laws, yet expressing turbulence, chaos, and unpredictability on unimaginable scales. Quasars challenge the notion that the universe is quiet, stable, or comprehensible through everyday intuition. They expose a reality driven by extremes, extreme gravity, extreme energy, extreme time, and invite us to rethink what it means to understand anything at all. Time is the first philosophical boundary quasars force us to cross. When we observe a quasar billions of light years away, we are seeing it not as it is, but as it was, often before the Earth existed, before the Sun formed, before the Milky Way had completed even a fraction of its evolution. The light that reaches us today began its journey when the universe was young, dense, and chaotic. In this sense, quasars collapse the distinction between past and present. They remind us that the cosmos is not arranged in a simple temporal sequence, but in overlapping layers of time stretched across space. Quasars reveal that the universe is a time machine, and every photon they send us is a message from an era long vanished. Observing them is an act of archaeology, but unlike terrestrial archaeology, we are not uncovering fossils. We are witnessing living, dynamic processes that occurred billions of years ago. This realization reshapes our understanding of existence. The past is not gone. It is simply far away. Quasars also challenge our concepts of scale. Human life is measured in decades, human civilizations in millennia, and human history in tens of thousands of years. But quasars live on timescales that dwarf every human measure. A quasar can remain active for tens of millions of years, feeding, shining, and shaping its environment. Its jets can stretch millions of light years, far larger than the galaxy that hosts it. Its accretion disk contains more mass than entire star clusters. These scales force us to acknowledge that much of cosmic reality operates outside our intuitive frame of reference. We are limited creatures living on a small planet, bound by the parameters of our biology. Quasars reveal that the universe is not built for our intuitions. Our intuitions must expand to grasp even a fraction of what the universe contains. There is also a philosophical tension in quasars between determinism and chaos. On one hand, the physics that governs accretion disks, relativistic jets, and gravitational dynamics is precise, mathematical, and predictable. General relativity describes the curvature of spacetime. Magnetohydrodynamics describes the behavior of plasma. Radiative transfer describes how photons escape from dense regions. But within these precise frameworks lie chaotic systems. Turbulence in the accretion disk is inherently unpredictable, driven by instabilities that amplify tiny perturbations. Jets wobble, fragment, and pulse in patterns that resist simple explanation. Variability in quasar emission arises from nonlinear processes that challenge even the most sophisticated models. This interplay between determinism and chaos mirrors deeper philosophical debates. Is the universe fundamentally predictable, or is it governed by chaotic processes that place limits on knowledge? Quasars suggest that both are true simultaneously. They demonstrate that the universe can be governed by elegant equations while still producing complexity that exceeds human predictive capacity. Reality itself becomes slippery when we consider the extreme environments around quasars. Near the event horizon, time slows, space bends, light orbits, physical. Laws merge into forms that defy classical intuition. Time dilation means that processes close to the black hole unfold more slowly relative to distant observers. Matter spiraling inward experiences a different temporal reality than matter farther out. Philosophically, this raises questions about the nature of time. Is it an absolute progression, or is it a local property shaped by gravity? General relativity asserts the latter, and quasars provide the observational evidence. Time becomes a landscape rather than a river. Quasars remind us that the fundamental structure of reality is layered, curved, and relative. Another philosophical implication lies in the origin of order. Quasars operate in environments full of chaotic collapse, extreme temperatures, supersonic turbulence, and magnetically dominated flows. Yet these chaotic environments produce structured outcomes: stable accretion disks, collimated jets, ionization cones, emission line regions arranged in measurable patterns. This emergence of order from our chaos mirrors a deeper theme in the universe. Structure arises not in spite of chaos, but because of it. Complexity is not an anomaly. It is a natural outcome of the laws governing matter and energy. Quasars, therefore, challenge philosophical notions that order requires design or intervention. They demonstrate that natural processes, given enough scale and time, can produce structures of immense complexity and beauty. There is also something deeply humbling about quasars. Their energy output dwarfs the combined luminosity of trillions of suns. Their gravitational influence shapes galaxies. Their lifetimes stretch across epochs beyond human comprehension. Yet their engines, supermassive black holes, are governed by the same physics that applies everywhere in the universe. They are not supernatural or inexplicable. They are extreme expressions of natural laws. This duality, extreme yet natural, invites reflection on humanity's place in the cosmos. We are not the center of the universe. We are one species on one planet, orbiting one star among hundreds of billions, in a galaxy that is itself one of trillions. Yet despite our smallness, we are capable of understanding quasars, decoding their spectra, simulating their dynamics, predicting their behavior, and using them to map the structure of the universe. This ability to comprehend reality at such enormous scales is not trivial. It is one of humanity's greatest achievements. Quasars also raise questions about the nature of existence and identity. A quasar is not a single object, but a combination of components. A black hole, an accretion disk, a corona, jets, winds, and a host galaxy. If any one of these components disappears, the quasar as we understand it ceases to exist, yet the black hole remains. So what is a quasar fundamentally? Is it the engine, the light, the emergent process of accretion, or is it the phenomenon produced by the interaction of all components? This mirrors philosophical debates about identity. Is something defined by its essence or by its behavior? A quasar's identity is not static, it changes over time. It brightens, fades, transforms, and eventually dies. In this sense, quasars possess a kind of cosmic life cycle, echoing patterns found across nature. Even more intriguing is the idea that quasars serve as cosmic mirrors. They reflect not only the physics of the universe, but our attempts to understand it. When we first discovered quasars, we could not understand their redshifts. When we learned their distances, we doubted their luminosities. When we accepted their luminosities, we questioned whether black holes could exist. When we accepted black holes, we questioned whether accretion could produce such energy. Each stage of quasar research has forced us to examine our assumptions, revise our theories, and confront the boundaries of knowledge. In this sense, quasars are more than astronomical objects. They are catalysts for intellectual growth. They also raise existential questions. If quasars are visible across billions of years, how many civilizations might have arisen and fallen in the time their light has traveled to us? How many galaxies evolved, merged, and changed while the photons from a quasar crossed the cosmic void? Quasars remind us that we are temporary observers in a universe with timescales far larger than our own. Yet our ability to perceive and analyze such phenomena gives meaning to our brief existence. We may be small, but we are capable of understanding the vast. As we explore the philosophical implications of quasars, we confront the question of whether the universe is comprehensible at all. Quasars represent the extreme frontier of that question. They embody the most powerful forces, the deepest gravitational wells, the most violent environments, and the earliest epochs. Yet even here, the human mind reaches, grasps, and deciphers. This suggests a profound philosophical truth. The universe is not obligated to make sense to us, yet it does. Our ability to understand quasars implies a compatibility between human cognition and cosmic order, a compatibility that remains one of the greatest mysteries of all. Ultimately, quasars show that the universe is both violent and creative, chaotic and ordered, terrifying and beautiful. They show that destruction can produce illumination, that collapse can create structure, and that the darkest objects can produce the brightest light. They show that the universe is not static, but alive with processes that shape galaxies, alter environments, and transform the cosmos on grand scales. They show that reality is far larger, stranger, and more intricate than our ancestors ever imagined. Every journey through the universe eventually leads back to ourselves, not in the sense of placing humanity at the center of creation, but in the recognition that our quest to understand the cosmos is also a quest to understand what it means to exist at all. Quasars, those titanic furnaces burning at the edges of cosmic time, are among the most distant and powerful teachers we have. They show us the birth pangs of galaxies, the seeds of cosmic structure, the extremes of gravity, the limits of matter, and the echoes of creation itself. They have illuminated not only the sky, but our understanding of how the universe formed, evolved, and continues to transform. As we trace their light across billions of years, we see a reflection of the universe's story, and in a smaller but no less meaningful way, a reflection of our own. A quasar begins with collapse, the collapse of a massive gas cloud, the collapse of a galaxy into its center, the collapse of matter into a gravitational well so deep that not even light can escape. Yet from this collapse emerges not silence, but brilliance. A black hole feeds, the accretion disk ignites, the corona flares, and jets burst forth at nearly the speed of light. What seems at first like destruction becomes creation. In this sense, quasars embody one of the universe's deepest truths. Nothing is simply an ending. Every ending is a transformation, and every transformation carries the potential for something new. The collapse that forms a black hole becomes the engine that lights up half the universe. The matter that falls inward becomes the light that travels billions of years to reach our telescopes. The galaxy disrupted by a quasar becomes the galaxy that grows, stabilizes, and evolves. The light we see from quasars is ancient, but it is not irrelevant. It tells us about eras long gone, but those eras shaped the conditions that made our own existence possible. The heavy elements forged in early stars and distributed by quasar-driven winds eventually became the foundations of planets, oceans, atmospheres, and life. The structure of the cosmic web, mapped in part through quasar absorption lines, determined where galaxies would form, how they would cluster, and how they would evolve. The quenching of star formation in massive galaxies, driven in part by quasar feedback, created the stable, mature galactic populations that populate the modern universe. The earliest quasars, blazing when the universe was young, helped ionize hydrogen and helium, sculpting the intergalactic medium through which later generations of stars and galaxies would grow. Without quasars, the universe would be chemically poorer, structurally different, and perhaps less conducive to life as we know it. Yet despite their influence, quasars are temporary. They flare, they feed, they reshape their environments, and after millions of years, they fade. Their accretion disks drain, their jets weaken, their radiation diminishes, and the once blazing nucleus dims to quiet darkness. Their black holes remain, silent and invisible, unless disturbed by new fuel. In this silence lies another truth. Even the brightest lights in the universe do not last forever. Their brilliance is temporary, but the effects of their existence are not. The galaxies they sculpt, the gas they heat, the metals they distribute, and the structures they influence persist long after the quasar itself has vanished. This concept echoes through the cosmos. Transient phenomena can have permanent consequences. Fleeting brightness can shape eternal darkness. Processes that last millions of years can influence structures that last billions. As we stand on Earth, observing quasars through the delicate mirrors of telescopes, we're reminded that the universe is not just immense but connected. Light from a quasar travels through cosmic filaments, past galaxy clusters, through voids, around dark matter halos, across regions of ionizing hydrogen, through expanding spacetime, and finally into our atmosphere, striking a sensor or an eye. The fact that this journey is possible at all speaks to the coherence of natural laws across billions of years and billions of light years. The photons we capture today left their source before Earth existed. They crossed epochs of cosmic evolution, surviving interactions expansion, and redshift. They arrive carrying encoded information about the universe's early conditions. They are messages from a time long before time mattered to us. Quasars also reveal how much we still do not know. Despite their brightness, they remain mysterious. We understand their basic engines, but not the details of jet formation, accretion stability, corona geometry, or early black hole seed formation. We know they influenced ionization, but not exactly how much. We know they quenched star formation, but not through which dominant mechanism. We know they must be linked to dark matter halos, but not precisely how feedback shapes halo evolution. In their extremes, quasars expose gaps in our theories, places where general relativity and quantum mechanics have not yet been reconciled, where plasma physics is still incomplete, where cosmology requires refinement. In the roaring accretion flows and violent jets of quasars, the universe reveals not only its power, but its cryptic depth. There are secrets encoded in their light curves, their spectral lines, their variability, and their structures, secrets that will take generations to decode. And yet, for all their scientific importance, quasars are also reminders of something profoundly human. We are creatures who evolved on a small planet, orbiting an ordinary star in a modest galaxy. Yet we dare to gaze across billions of years, decode the behavior of objects beyond imagination, and weave coherent narratives from faint photons that left their sources before the first humans walked on Earth. This ability to extract meaning from the deepest reaches of the cosmos is one of the defining achievements of human consciousness. Quasars show us not only the universe's grandeur, but our capacity to understand that grandeur. They show us that the mind is not confined by its biological origins. It can expand to encompass processes that occur on scales of millions of light years and millions of years. The fact that human beings can comprehend quasars is, in itself, a philosophical revelation. There is also an emotional dimension in studying quasars. Their light is beautiful, not just scientifically, but aesthetically. The swirling accretion disks, the collimated jets, the glowing ionization cones. These structures evoke awe. They remind us that the universe is not merely functional, but spectacular. It contains patterns that resonate with human perception, symmetry that feels almost artistic, and scales that evoke wonder rather than fear. The sense of humility and awe that quasars inspire is not a distraction from scientific study. It is a companion to it. Wonder is the catalyst of curiosity, and curiosity is the engine of discovery. In contemplating quasars, we also contemplate the arc of cosmic history. The universe began in darkness, expanded, cooled, and produced the first stars. From these stars came galaxies, and from galaxies came black holes, and from black holes came quasars, cosmic lighthouses illuminating the fog of the early universe. Eventually, quasar numbers peaked and declined, giving way to a quieter cosmic era dominated by mature galaxies. This narrative mirrors cycles found everywhere in nature: birth, growth, transformation, decline. But the decline of quasars is not a story of disappearance. It is a story of evolution. Their legacy remains etched into the structures of galaxies and the chemical composition of the universe. Their influence continues even in absence. As humanity builds the next generation of telescopes, detectors, and simulations, quasars will once again become central to discovery. We will see farther, hear deeper, simulate more precisely, and test theories more rigorously. We will uncover quasars from the earliest epochs, observe black hole mergers through gravitational waves, resolve accretion disks at event horizon scales, and map cosmic structures more accurately than ever before. Quasars will accompany us into the next era of scientific advancement, guiding our understanding as they have for decades. But even as technology evolves, the essence of our inquiry remains the same: a desire to understand where we come from, What shaped our universe, and what forces govern existence? Quasars, in all their brightness and ferocity, in all their philosophical weight and scientific significance, are part of that story. They are reminders that the universe is larger, stranger, more beautiful, and more intricate than any single human life can encompass. Yet through science, we touch that vastness. We interpret it. We learn from it. In the end, the story of quasars is a story about illumination, not only in the literal sense, as cosmic beacons, but in the metaphorical sense. They illuminate the universe, but they also illuminate our understanding. They reveal how complexity emerges from chaos, how structure arises from collapse, how the darkest objects create the brightest light, and how the universe evolves from youthful turbulence to mature structure. And most importantly, they reveal something about us, that curiosity is an unquenchable flame, that knowledge is an expanding frontier, and that even from our small corner of the cosmos, we can look outward and comprehend the vast. As the light of quasars fades into the deep night of cosmic time, new questions arise. What other phenomena await discovery? What mysteries lie beyond the observable universe? What processes occurred in epochs we cannot yet see? And what role will human beings play in the unfolding story of cosmic exploration? The universe will continue its evolution, indifferent to our presence, yet open to our understanding. And as long as we continue to observe, think, question, and imagine, quasars will remain part of our intellectual and emotional heritage, symbols of the universe's power and the human mind's resilience. This is the final lesson of quasars, that the universe is an interplay of darkness and light, creation and destruction, order and chaos, and that meaning emerges not from the universe itself but from our drive to understand it. The light of quasars may be ancient, but the insight they provide is timeless.